Hello, friend. Welcome back. Or if this is your first time drifting here with us, welcome home. Some nights the sky feels wider than it should. Stars breathe slower. Time folds in on itself, quiet and endless. And sometimes, just sometimes, something passes through that doesn't belong to now. Something older. Something that remembers when the universe was younger, wilder, less certain of what it would become. On July 1st, 2025, we found one of those things, a comet. But not just any comet. This one might be older than the sun itself, older than Earth, older than every planet you've ever known. It came from a part of the galaxy we've never seen up close before, carrying stories written in ice and dust, stories that began when our solar system was nothing but a dream in a cloud of gas. Its name is 3IATLAS, and tonight we're going to follow it home. Before we begin this quiet journey together, if you find comfort in these moments and stories told softly under distant stars, you might like to stay a while. You can gently tap the like button, not for the algorithm, but as a small way of saying you were here, that this mattered. Subscribe if you'd like more nights like this, one more whispers from the edge of what we know, and ring the little bell not for noise, but so the next quiet story can find you again when you need it most. We're grateful you're here. Now, let's drift. Picture this. You're standing outside on a summer night in 2025, somewhere far from city lights. The Milky Way stretches overhead like a river of forgotten time. You're looking south toward the constellation Sagittarius, toward the heart of our galaxy, where stars crowd together in ancient multitudes. And passing through that sea of light, invisible to your eyes, but not to the machines we've built to see further than we can, is something that shouldn't be there. Something moving at 140,000 miles per hour. Something that has been moving for longer than our sun has been burning. Scientists call it 3IATLAS. The 3I means it's the third confirmed interstellar object. A visitor from another star system unbound by our sun's gravity just passing through. The Atlas part comes from the telescope that found at the asteroid terrestrial impact last alert system, stationed high in the Chilean mountains, where the air is thin and the stars feel close enough to touch. But names are just labels we give to mysteries we're trying to understand. What 3IATLAS really is, what it really means is something far stranger and more beautiful than a catalog number could ever capture. It's a messenger, a time capsule, a fragment of the galaxy's deep past drifting through our present on its way back to silence. When the detection came through on that July morning, it appeared as a dim smudge of light on digital sensors, magnitude 18, far too faint for human eyes, but bright enough for patient machines. It was 325 million miles from Earth, 420 million miles from the Sun, moving along the border between Serpens Cauda and Sagittarius near the galactic plane. That location matters. The galactic plane is where most of the Milky Way's stars live, a flat disk of light and matter spinning through the darkness. Our sun lives there too, in what astronomers call the thin disk, the younger, more metal-rich layer of the galaxy. But 3IATLAS wasn't following the rules of the thin disk. Its path was tilted steep, cutting through the galactic plane at an angle that told a different story. It was moving upward through space at a velocity we'd never seen before, in an interstellar visitor rising above the disk, like something surfacing from deep water, something that belonged to an older, deeper layer of the galaxy's structure. The speed alone was remarkable, 61 kilometers per second relative to the sun. That's the kind of velocity that can't be explained by a gentle nudge from a planet's gravity. That's the signature of something that has been falling through the galaxy's gravity well for billions of years, picking up speed, losing speed, trading momentum with stars and nebulae. It passed too close to, until finally by chance, and by the mathematics of celestial mechanics, its path intersected with ours. We didn't capture it. We didn't pull it in. We were simply there when it passed by like two strangers on a long road meeting once, and never again. Do you ever wonder what it means to be old? Not old in human terms, not decades or even centuries, but old in the way the universe measures time. Old enough to have seen stars born and die. Old enough to have drifted past solar systems that no longer exist. Old enough that the atoms in your body were forged in different stars than the atoms in everything around you. That's the kind of old we're talking about with 3IATLAS. If the estimates are right, and there's a 2 in 3 chance they are, this comet is somewhere between 7 and 14 billion years old. Our sun is 4.6 billion years old. Earth is 4.54 billion. The oldest rocks we've ever found on Earth, tiny zircon crystals that survived the planet's violent youth, are 4.4 billion years old. 3IATLAS predates all of it. It was already ancient when our solar system was nothing but a cold, dark cloud of hydrogen and dust, slowly collapsing under its own gravity. Not yet aware it would one day birth a star called Sol, and a small blue world where creatures would eventually look up and wonder about visitors from the deep past. How do we know this? How can we possibly measure the age of something that came from another star that has no birth certificate, no parent we can trace back to, no clear origin point we can map? We do it through motion, through trajectory, through the mathematics of orbital mechanics, and the patient work of building models that simulate how objects move through the galaxy over cosmic time. A young astronomer named Matthew Hopkins spent years developing one such model during his doctoral research at the University of Oxford. He called it the Otautahi-Oxford model, a predictive framework that uses data on cometary orbits and stellar populations to estimate where interstellar objects come from and how old they might be. He defended his thesis on June 24, 2025. 1 week later, 3IATLAS was discovered. 1 week. Imagine that. You spend years building a theoretical model to predict the properties of things that might not even exist, things we've only seen twice before in all of human history. You defend your work. You're ready to rest, to take a breath, maybe take a vacation. And then the universe delivers exactly what you predicted right on schedule, as if it had been waiting for you to finish your equations before making its entrance. Hopkins didn't go on vacation. He stayed, he worked. He applied his model to the real-time data streaming in from telescopes around the world. And what he found was extraordinary. 3IATLAS, based on its velocity components and trajectory through the galaxy, most likely originated from what astronomers call the thick disk. Not the thin disk where we live, where most of the Milky Way's younger stars reside, but the thick disk, a population of ancient stars that orbit above and below the galactic plane, stars that formed when the galaxy was younger, when there had been fewer generations of supernovae to scatter heavy elements through space, when the universe was still learning how to make planets and comets, and eventually, improbably, us. The thick disk is a graveyard and a museum. It's where the galaxy's oldest stars go to slowly fade, orbiting in tilted paths that take them high above and below the plane, watching the younger generations spin below them. If 3IATLAS formed around one of those stars, if it was born in a protoplanetary disk, orbiting a sun that ignited when the universe was only a few billion years old, then it has seen things we can barely imagine. It has witnessed the galaxy evolve. It has drifted past stars that exploded and became black holes. It has felt the gravitational pull of nebulae that no longer exist. It has traveled alone and in silence for longer than our entire solar system has existed. And now it's here. Now we can see it. Now we can study it. Now we can ask it questions, even if the answers take years to decode. Professor Chris Lintott, an astrophysicist at Oxford and a co-author on the study, with Hopkins, put it simply, this is an object from a part of the galaxy we've never seen up close before. We think there's a 2/3 chance this comet is older than the solar system, and that it's been drifting through interstellar space ever since. 2/3, 67% confidence. In science, that's not certainty, but it's strong. It's the difference between a guess and an informed conclusion based on the best data we have. It means that more likely than not, the thing we're looking at in our telescopes tonight, The thing that's currently somewhere between the orbits of Earth and Mars, making its closest approach to the Sun it will ever make, is older than the ground beneath your feet, older than the oceans, older than the moon, older than every fossil, every mountain, every continent that ever drifted across Earth's surface. There's something humbling about that, isn't there? Something that puts our brief flickering existence into perspective. We live for decades. We build civilizations that last for centuries, maybe millennia if we're lucky. We think in terms of historical time, of things that happened 1,000 years ago, 2,000, maybe 10,000 if we're talking about the end of the last ice age. But 3IATLAS is operating on a different scale entirely. It's geological time multiplied by 1,000. It's cosmic time. It's the kind of time that makes human history look like a single breath in a very long, very patient story. And yet, despite its age, despite the unimaginable distance it has traveled, 3IATLAS is not so different from the comets we know. It has ice. It has dust. It has a nucleus, a solid core made of frozen volatiles and rocky material held together by its own weak gravity. As it approached the Sun in the summer and fall of 2025, that ice began to sublimate, turning directly from solid to gas without passing through a liquid phase the way dry ice does on Earth. That gas carried dust with it, forming a glowing cloud around the nucleus called a coma, and a tail that stretched behind it like a memory. This is what comets do. This is their nature. They are ice and stone wandering the dark, waiting for the warmth of a star to wake them up and make them beautiful for a brief moment before the cold returns. But there's something different about 3IATLAS, something that sets it apart from every other comet we've studied. It's the chemistry, the composition, the specific mixture of elements and molecules that make up its ice and dust. Because if it formed around an ancient star in the thick disk, a star with lower metallicity than the Sun, a star born before the galaxy had been enriched by as many generations of supernovae, then its chemistry should reflect that. It should have less of certain heavy elements. It should have more water ice, more simple molecules, fewer complex carbon compounds. And so far, that's exactly what we're seeing. Early spectroscopic observations suggest 3IATLAS is water-rich incredibly so, producing hydrogen cyanide at a rate of several kilograms per second as it heats up near the Sun. That's not unusual for a comet. What's unusual is the ratio, the balance, the signature of an environment we've never sampled before, an environment that existed billions of years before ours did. We'll talk more about the chemistry later, about what the specific molecules tell us about the strange abundance of nickel and iron, about the carbon dioxide levels that suggest formation in an extremely cold region, far from a star. But for now, just hold this thought. We are looking at something that formed under different rules in a different epoch when the galaxy was a different place. We are reading a message from the deep past written in a language of atoms and ice, and we're only just beginning to learn how to translate it. The discovery of 3IATLAS is rare, but it's not unique. It's the third confirmed interstellar object we've detected, which means we're starting to build a sample size, starting to see patterns, starting to understand that the space between stars is not empty. It's full of wanderers, full of fragments cast out from dying solar systems, from stars that went supernova, from planetary systems that became unstable and ejected their icy debris into the galactic ocean. We have known this theoretically for decades, but only recently have our telescopes become sensitive enough to catch these visitors as they pass through. The first was 1is Oumuamua, discovered in 2017, a strange elongated object that moved too fast and accelerated in ways we didn't expect, sparking endless speculation and debate. The second was 2I Borisov, discovered in 2019, a more conventional comet that looked and behaved much like the comets in our own solar system, giving us our first clear comparison between interstellar and solar system chemistry. And now, 3IATLAS, the oldest of the three, the one that came from furthest away, not in terms of distance, but in terms of time. What does it mean that we're finding these objects now, after thousands of years of looking at the sky? It means our tools have finally caught up to our curiosity. It means we're living in a moment of transition, where the space between stars is becoming accessible to us, not through travel, not yet, but through observation. We can see further, we can see fainter, we can track faster-moving objects and measure their chemistry from millions of miles away. And as our tools improve, we'll find more. The Vera C. Rubin Observatory, currently preparing to begin its legacy survey of space and time, is expected to discover between 5 and 50 interstellar objects over the next decade. Maybe more if the discovery of 3IATLAS is any indication. Each one will be a new data point, a new piece of the puzzle, a new story, from a part of the galaxy we've never touched. But even as we find more, even as these visitors become less rare and more expected, there's something about 3IATLAS that will always feel singular. It was the first one we found that's definitively measurably older than our solar system. The first one that forces us to confront the reality that we're not just seeing other solar systems, we're seeing other epochs, other eras, other chapters in the galaxy's long, slow evolution, from chaos to structure to whatever comes next. There's a moment in every discovery where the facts settle in and become real, where the numbers stop being abstract and start being something you can almost touch. For some of the astronomers working on 3IATLAS, that moment came when they realized what the age estimate meant. 7 billion years, 10 billion, maybe more. That's not just old. That's ancient, that's primordial, that's closer to the Big Bang than it is to us. The universe itself is only 13.8 billion years old. If 3IATLAS is 12 or 13 billion years old, it formed when the universe was less than 2 billion years old, during an epoch called cosmic noon, when star formation was at its peak, when galaxies were colliding and merging and creating stars at a rate that will never be matched again. It might have witnessed that. It might carry chemical signatures from that era, from a time when the universe was hotter, denser, more violent, more alive with possibility. And now it's here. Now it's passing through our small corner of space, briefly illuminated by our young sun, observed by creatures who have only been looking up with understanding for a few thousand years. It will stay visible for a few more weeks, fading as it moves away, heading back out into the darkness from which it came. By late January 2026, it will be too faint for ground-based telescopes to track. And then it will be gone, continuing its journey through the galaxy, traveling for another few billion years, until perhaps by chance it passes through another solar system where other beings might look up and wonder what it is where it came from, what stories it carries. But for now, for this brief moment, it's ours to study, ours to marvel at, ours to learn from. And what we're learning is extraordinary. So, tonight as we begin this journey together, as we follow 3IATLAS from its discovery to its departure, from the chemistry of its ice to the mechanics of its orbit, from the questions it raises to the answers it might provide, I want you to hold on to this feeling, this sense of scale, this awareness that time is deeper and stranger than we usually allow ourselves to believe. We live in the present, but the present is built on layers of past that go down further than we can easily imagine. And sometimes, rarely, something from those deep layers surfaces and passes by. And if we're paying attention, if we're patient and curious and willing to listen, it speaks to us. 3IATLAS is speaking. Let's listen. The journey we're about to take will move through 9 quiet stations, 9 ways of understanding what this ancient visitor means. We'll trace its path backward through space and time, trying to imagine where it came from. We'll decode its chemistry, reading the story, written in the ratios of ice and dust. We'll watch it change as the sun warms it, activating jets of gas that have been dormant for billions of years. We'll see how telescopes around the world and in space turn toward it, capturing light that had bounced off its surface light, that carried information coded in wavelengths and spectra. We'll think about what it means, what we can learn from it, what it teaches us about the galaxy and about ourselves. And at the end, we'll say goodbye, watching it fade back into the darkness, knowing we were lucky to see it at all. But first, before we move deeper into the story, we need to understand the moment of discovery itself, because every great finding begins with a single observation, a single pixel of light that's out of place, a single signal that shouldn't be there. And the story of how we found 3IATLAS is its own kind of miracle, a convergence of timing and technology and human persistence that almost didn't happen. Let's drift now into that July morning in Chile, where the desert is cold and the stars are sharp, where telescopes scan the sky in search of threats and wonders, where a computer algorithm flagged something unusual moving through Sagittarius, and where thousands of miles away, a young astronomer who had just finished his thesis was about to have the theoretical work of years meet the reality of discovery. There's a place in Chile where the sky opens wider than anywhere else on Earth, the Atacama Desert, the driest place on the planet where some weather stations have never recorded rain, where the air is so thin and clear that stars don't twinkle, they burn steady and sharp like holes punched through black paper. It's here in this landscape that looks more like Mars than Earth that we've built some of our most sensitive eyes. Telescopes that watch, telescopes that wait, telescopes that scan the same patches of sky night after night, looking for anything that moves, anything that changes anything that shouldn't be there. On July 1st, 2025, at the Atlas facility near Rio Hurtado, one of those telescopes found something that would change how we think about the age of things. It found 3IATLAS, and the story of that discovery, the timing of it, the sheer improbability of it, is almost as remarkable as the object itself. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. It's not designed to find ancient comets from the thick disk of the galaxy. It's designed to find rocks that might hit Earth, asteroids on collision courses, near-Earth objects that could pose a threat. It's a planetary defense system, essentially a network of 4 telescopes spread across 2 hemispheres, taking images of the entire visible sky multiple times each night, comparing those images to detect motion. Anything that moves between frames gets flagged. Most of what it finds is mundane. Known asteroids, satellites, cosmic rays hitting the detector. But occasionally, very occasionally, it finds something new, something no one has ever seen before. On that July night, the telescope at observatory code W68 captured a moving object at apparent magnitude 18. For context, magnitude 18 is about 40,000 times fainter than what the naked eye can see. It's the kind of faint that requires not just a telescope, but a big telescope and patient software and perfect conditions. The object was located 3.5 astronomical units from Earth. 1 AU is the distance from Earth to the Sun, about 93 million miles. So this thing was 325 million miles away, almost as far as Jupiter gets from us. And we could still see it. Not because it was bright, but because we were looking in the right place at the right time with the right tools. The first images showed a faint smudge, not a point of light like a star, but something extended, something fuzzy. That fuzziness matters. It's one of the first clues that you're looking at a comet rather than an asteroid. Asteroids are solid rock and metal, reflecting sunlight like tiny moons. Comets are ice and dust, and when they get close enough to the sun, that ice starts to evaporate, creating a cloud of gas and particles around the nucleus. That cloud, the coma, scatters sunlight and makes the comet look fuzzy, diffuse, ghostly. Even at magnitude 18, even at 325 million miles, the Atlas was already showing cometary activity. Already awake, already responding to the distant warmth of the sun. The automated software flagged it immediately. New object, moving fast, designation pending. And then the real work began. When you find something new in the sky, the first thing you need to do is track it, get more observations. Pin down its position as precisely as possible. Calculate its orbit. Figure out where it came from and where it's going. This is harder than it sounds. Space is big. Objects move in 3 dimensions along curved paths determined by gravity. One observation gives you a position. 2 observations give you motion. 3 observations start to define an orbit. But you need more than 3. You need dozens, hundreds if possible, from multiple sites over multiple nights to really nail down the trajectory. And you need to do it fast, because the object might not stay visible for long. It might fade. It might move behind the sun. It might leave the inner solar system and disappear back into the darkness before you figured out what it is. So, astronomers around the world got to work. Telescopes in Chile, Hawaii, Arizona, Spain, South Africa. Professional observatories and amateur setups. Anyone with a decent scope and a clear sky started contributing data points. Position measurements, brightness estimates, spectroscopic observations to determine composition. Within days, they had enough information to calculate a preliminary orbit. And that's when things got interesting. The orbit was hyperbolic, not elliptical like the orbits of planets and most comets and asteroids in our solar system, but hyperbolic and open curve, a path that comes in from infinity and returns to infinity, never closing, never repeating. In orbital mechanics, this is the signature of something that's not bound to the sun, something that has enough velocity to escape the solar system entirely. There are a few ways an object can end up on a hyperbolic orbit. It could be a comet from the Oort cloud, the distant sphere of icy bodies surrounding the solar system that got perturbed by a passing star or a gravitational interaction and fell inward, picking up so much speed on its way to the sun that it'll never return. That happens occasionally. Or it could be something that passed close to Jupiter, or another massive planet got a gravitational kick and was flung outward on an escape trajectory. That happens too. But 3IATLAS didn't fit either of those scenarios. Its orbit was too steep, its velocity was too high, and critically, when astronomers traced its path backward, projecting where it had come from before entering the solar system, they found that it hadn't passed close to any of the giant planets. It hadn't gotten a gravitational boost from Jupiter or Saturn or Neptune, which meant its high velocity had to be intrinsic. It had to come from outside. It had to be interstellar. The numbers were striking. When 3IATLAS entered the solar system, it was moving at 61 kilometers per second relative to the sun. That's about 136,000 miles per hour. Fast enough to cross the distance from Earth to the Moon in less than 2 hours. Fast enough that no plausible gravitational interaction within our solar system could explain it. And the direction mattered too. It was coming from the south, from the direction of Sagittarius, from near the galactic center, moving against the flow of local stellar traffic. Most stars in our neighborhood, including the sun, orbit the galactic center in roughly the same direction, like cars on a highway. But 3IATLAS was cutting across lanes, moving on a tilted path, rising upward through the galactic plane, with a vertical velocity component that was unusually high, 18.5 kilometers per second in the vertical direction, measured perpendicular to the galactic disk. That's fast. That's the kind of velocity you see in stars, from the thick disk, old stars, with eccentric orbits that take them high above and below the plane. And if 3IATLAS was moving like a thick disk object, it probably came from the thick disk, which meant it was probably very, very old. This is where Matthew Hopkins enters the story. Hopkins was a doctoral student at the University of Oxford, working under Professor Chris Lintott, studying the properties of interstellar objects, and trying to build predictive models for what we might expect to find as our detection capabilities improved. He'd spent years developing what he called the Ōtautahi Oxford model, named after the Maori name for Christchurch, New Zealand, where he'd done part of his research. The model was ambitious. It tried to simulate the population of interstellar objects in the galaxy based on stellar demographics, cometary formation rates, ejection mechanisms, and galactic dynamics. It made predictions about how many interstellar visitors we should expect, what sizes they'd likely be, what compositions, what ages, what trajectories. And crucially, it suggested that most interstellar objects we'd found so far, like Oumuamua and Borisov, came from the thin disk from relatively young stellar populations similar to our own. But the model also predicted that if we kept looking, we'd eventually find objects from the thick disk, older objects, ancient objects, objects that formed when the galaxy was fundamentally different. Hopkins defended his thesis on June 24th, 2025. He'd passed, the work was done. He was planning to take some time off, maybe travel decompress after years of intensive research. And then, 7 days later, 3IATLAS was announced. 7 days. Imagine finishing a theoretical framework that predicts something rare and unexpected, something that might take decades to find, and then having reality deliver it to you a week later, right when you're about to log off and take a break. It's the kind of timing that makes you believe the universe has a sense of humor. Hopkins didn't take a break. He stayed. He pulled up the orbital data, he ran it through his model, and what came out was extraordinary. Based on the velocity components, the galactic trajectory, the steep inclination, the Otau-Tahi-Oxford model estimated that 3IATLAS had a 68% probability of originating from the thick disk. And if it came from the thick disk formed around one of those ancient stars, then it was likely between 7.6 and 14 billion years old. Older than the Sun, older than Earth, older than anything in our solar system, except for a few pre-solar grains, microscopic dust particles that condensed in the outflows of stars that died before the Sun was born. Grains that we find embedded in meteorites, relics of a time before our time. 68%, 2/3 probability, not certainty but strong likelihood. In science, especially in astrophysics, where direct measurement is often impossible and we have to rely on models and statistics and inference, 68% is robust. It's the difference between speculation and evidence-based conclusion. Other teams ran independent analyses and got similar results. Astor Taylor and Daryl Seligman, working separately, estimated an age of 3 to 11 billion years, broadly consistent with Hopkins's range. The numbers converged. The conclusion held. 3IATLAS was very likely the oldest comet ever observed by human beings. Let's pause here and think about what that means. Every other comet we've studied, from Halley's Comet to Hale-Bopp, to the hundreds of smaller ones that pass through the inner solar system each year, formed at the same time as our solar system, about 4.5 billion years ago. They're fragments of the protoplanetary disk leftovers from the process that made the sun and planets ice and rock, that never coalesced into worlds that got scattered into distant orbits, where they've remained mostly unchanged for billions of years. When we study those comets, we're studying our own origins. We're reading the chemical record of the nebula from which we came. But when we study 3IATLAS, we're reading a different record. A record from a different place, a different time, a different chapter in the galaxy's history. It's like the difference between studying your own family tree and finding a letter written by someone from a completely different lineage, a lineage that predates your own by thousands of generations. The discovery was announced publicly in mid-July, and it sent ripples through the astronomy community. Conference talks were hastily rescheduled. Observing proposals were rushed through. Telescopes that had been allocated for other projects were redirected, because this was a rare opportunity. Interstellar objects don't visit often. We've only confirmed 3 ever. And this one, this ancient wanderer, was passing through right now, right in front of us, visible and available for study for a limited time, before it faded and left, and took its secrets with it. Every major telescope that could observe it did. Hubble, the grand old workhorse of space-based astronomy, captured images of the comet's coma on July 21st, showing a fuzzy cloud of gas and dust surrounding an invisible nucleus. The James Webb Space Telescope, the most powerful infrared observatory ever built, trained its instruments on 3IATLAS on August 6th, breaking down the light into spectra, measuring the specific wavelengths absorbed and emitted by molecules in the coma, trying to identify what it was made of. Ground-based observatories like the Very Large Telescope in Chile, the Gemini telescopes, the Keck Observatory in Hawaii, all took turns observing. Even spacecraft not designed for comet observation got involved. NASA's Stereo mission, designed to watch the sun, caught glimpses of 3IATLAS as it passed through the inner solar system. The ExoMars Trace gas orbiter circling Mars snapped a picture of the comet in the Martian sky, a perspective no human had ever seen before. And what did all these observations reveal? Complexity, strangeness, familiar cometary behavior with subtle differences that hinted at an alien origin. The coma was active, producing jets of gas and dust. But the structure of those jets was unusual. They wobbled. They precessed, rotating slowly over time in a pattern that suggested the nucleus was tumbling, spinning on an axis that wasn't stable. Astronomers at the Tide Observatory in Tenerife tracked the jets over 37 consecutive nights in August and September, measuring their positions, their brightness, their evolution. They found that the rotation period was about 15.5 hours, with jets shifting orientation every 7 hours and 45 minutes, exactly half the rotation period. This suggested the nucleus wasn't a simple sphere, but an irregular, elongated shape, maybe a contact binary, two lobes stuck together, spinning slowly and unevenly as it traveled through space. That's not unusual for comets. Many have irregular shapes, but the stability of the jet pattern was unusual. Most comets show chaotic, unpredictable outgassing. 3IATLAS showed structure, persistence, jets that turned on and off in regular cycles as if the nucleus had specific active regions that faced the sun at specific times during its rotation. That kind of behavior suggests a strong, cohesive interior, not the loosely bound rubble pile we often see in cometary nuclei. It suggests an object that has held together structurally intact for a very long time. As 3IATLAS approached perihelion, its closest point to the sun on October 29th, the activity increased. The coma brightened. The tail grew longer, more defined, stretching away from the sun. In the classic cometary configuration, gas and dust, pushed by solar wind and radiation pressure. At perihelion, it was 1.36 astronomical units from the sun, about 126 million miles safely between the orbits of Earth and Mars. Not close enough to be dangerous, not close enough to evaporate entirely, just close enough to wake up, to become active, to give us a show. And what a show it was. Spectroscopic observations revealed the presence of familiar molecules. Water vapor, the most common volatile in comets, sublimating from ice as the sun's heat penetrated the surface. Carbon dioxide, another common ice, more volatile than water, evaporating even at greater distances from the sun. And hydrogen cyanide, a prebiotic molecule, a building block of more complex organic chemistry, something we see in many comets and in the interstellar medium. The presence of these molecules wasn't surprising. What was surprising was the ratios, the abundances, the balance between different species. Hydrogen cyanide production, for instance, was measured by the James Clerk Maxwell telescope in early September at about 1.5 times 10 to the 25th molecules per second. That's roughly 2.5 kilograms of HCN every second, streaming off the nucleus carried away by the solar wind. A week later, the rate had climbed to 4.5 times 10 to the 25th molecules per second. That's a lot. That's higher than most solar system comets show at comparable distances from the sun. It suggests a nucleus rich in volatile ices, not depleted by billions of years of slow sublimation in interstellar space. And that's strange, isn't it? If 3IATLAS is really 8 or 10 or 12 billion years old. If it's been drifting through the galaxy for all that time, exposed to cosmic rays, to the faint warmth of distant stars, to micrometeorite impacts, shouldn't it have lost most of its volatiles by now? Shouldn't it be a dead, inert rock, all the ice long since evaporated? The fact that it's still active, still producing gas and dust, at rates comparable to much younger comets, suggests either that it's been incredibly well preserved, spending most of its existence in extremely cold, stable regions, far from any star, or that our understanding of cometary aging is incomplete. There's another piece of the puzzle that doesn't quite fit the simple narrative. Spectroscopic observations detected unusually high emissions of nickel and iron. Both elements are common in comets present in dust grains and in the rocky component of the nucleus. But the ratio of nickel to iron in 3I-ATLAS was higher than what we typically see in solar system comets. Higher even than what was observed in 2I-Borisov, the previous interstellar comet. That's intriguing. Nickel and iron are products of stellar nucleosynthesis, forged in the cores of massive stars and scattered into space when those stars exploded as supernovae. The ratio between them depends on the specific conditions in the star that produced them, on the temperature and pressure and neutron flux during the supernova. If 3I-ATLAS has a different nickel to iron ratio than solar system comets, it suggests it formed from material processed through different supernova that happened earlier in the galaxy's history, when the mix of elements being produced was different. It's a chemical fingerprint, a signature of origin, a clue written in the specific proportions of metals in dust grains that condensed from the debris of exploded stars billions of years before our sun ignited. This is one of the things that makes 3I-ATLAS so valuable scientifically. It's not just an old comet. It's a sample of the ancient galaxy, a time capsule carrying information about conditions that existed long before our solar system formed. When we analyze its chemistry, we're not just learning about one object. We're learning about the evolution of the Milky Way, about how the abundance of elements changed over time as generations of stars lived and died, enriching the interstellar medium with heavier elements. We're learning about the protoplanetary disks that formed around ancient stars, what they were made of, what kinds of planets and comets they could produce. We're learning about processes that happened so long ago that all direct evidence has been erased, recycled through countless cycles of star formation and death, except for these rare wanderers that somehow survived, that escaped their parent systems and drifted into the present, carrying messages from the deep past. Think about the journey 3I-ATLAS must have taken to end up here. If it formed around a star in the thick disk 8 or 10 billion years ago, that star is likely gone now. Stars like the Sun last about 10 billion years before they run out of fuel, swell into red giants, and eventually shed their outer layers, leaving behind a white dwarf. If 3I-ATLAS is 8 billion years old and its parent star was similar to the Sun, that star might still be burning, might still be out there somewhere, moving through the thick disk on its own lonely orbit. But we can't trace 3I-ATLAS back to a specific star. The comet has been traveling through the galaxy for too long, subject to too many gravitational perturbations, too many close encounters with other stars and nebulae for us to reconstruct its exact trajectory. A 2025 study by Yiyang Guo found that 3I-ATLAS may have passed within 1 parsec, about 3.3 light-years of 25 known stars in just the past 10 million years. 1 parsec is close enough for significant gravitational interaction, close enough to change velocity, to alter trajectory, to scramble the orbital history. If that's happened 25 times in 10 million years, imagine how many times it's happened over 8 billion years. Hundreds of thousands of close encounters, maybe more. Each one shifting the comet's path, slightly erasing a little more of the record, until tracing back to the origin becomes impossible. It's like trying to find the source of a river by following a single drop of water that's passed through 1,000 streams and mixed with rain and evaporated and condensed and fallen again. The information is lost, diffused into the chaos of the system, but we can still make educated guesses. We can look at the velocity, the trajectory, the chemistry, and infer where it probably came from, even if we can't point to a specific star. And all the evidence points to the thick disk. to a region of the galaxy populated by stars that formed early that are metal poor compared to the sun that orbit on tilted eccentric paths. Stars that, if they had planets and comets, would produce planets and comets with chemical compositions different from ours. And that's what we're seeing. That's what the data is telling us. 3IATLAS is a thick disk comet, an ancient relic, a messenger from the galaxy's youth. The timing of its discovery just days after Hopkins defended his thesis, just as the Vera C. Rubin Observatory was preparing to begin operations, feels almost too perfect. Some discoveries happen by accident. Some happen because someone was looking for something specific and found it. This one happened because the theory predicted it, the technology enabled it, and the universe cooperated. It's a reminder that we're living in a unique moment in human history, a moment where our tools are finally sophisticated enough to detect phenomena we've only theorized about. Interstellar objects were predicted to exist long before we found the first one. Astronomers knew, based on models of planetary system formation and stellar dynamics, that solar systems must eject comets and asteroids, regularly casting them out into the galaxy to wander indefinitely. But knowing something exists theoretically and actually seeing it are different experiences. Oumuamua in 2017 was the proof of concept. Borisov in 2019 was the confirmation that it wasn't a fluke. And 3IATLAS in 2025 is the expansion of the paradigm, the discovery that pushes the boundaries further, that shows us the population of interstellar wanderers is more diverse, more ancient, more revealing than we initially imagined. And there will be more. The Rubin Observatory, with its 8-meter mirror and 3 billion pixel camera, is designed to survey the entire visible sky every few nights, capturing transient events and moving objects with unprecedented sensitivity. It's expected to find dozens of interstellar objects over the next decade, maybe 50, maybe more. Each one will add to the data set, refine the models, improve our understanding. But even as we find more, even as these discoveries become routine, there will always be something special about 3IATLAS, the first confirmed thick disk visitor, the oldest comet we've ever seen, the one that came at just the right time to validate years of theoretical work and launch a new era of interstellar object science. Before we move forward, before we dive deeper into the trajectory and the age estimates and the chemistry, it's worth sitting with this moment, the moment of discovery. The first images showing a faint fuzzy object moving against the stars, the realization that this wasn't just another comet, but something extraordinary. The calculations that revealed its age, its origin, its significance. The collective effort of hundreds of astronomers around the world, sharing data, comparing notes, building a picture of something none of them had ever seen before. This is how science works at its best. Patient observation, careful measurement, theoretical prediction meeting empirical reality. And in the middle of it all, a small icy body, older than continents, older than oceans, older than planets, drifting through our neighborhood, on its way back to the dark, giving us a brief window to study it, to learn from it, to marvel at the sheer improbability of its existence and our ability to perceive it. We found it. Against all odds in the vastness of space and the depth of time, we found it. And now, we're going to follow it. The trajectory awaits the mathematical story of how an 8 billion-year journey brought this ancient wanderer to our doorstep, and what that path tells us about the hidden architecture of the galaxy itself. Orbits are stories written in mathematics. Every curve, every angle, every velocity tells you where something has been and where it's going. They're maps carved by gravity paths drawn through space by the invisible hand of mass-bending space-time. When you look at an orbit, you're not just seeing geometry, you're seeing history. You're seeing cause and effect, playing out over cosmic distances and time scales. And when the orbit is hyperbolic, when the curve doesn't close, when the path comes from infinity and returns to infinity, you're seeing something even more profound. You're seeing an escape, a departure, a journey that began somewhere we can't see and will end somewhere we'll never reach. The orbit of 3IATLAS is one of the most extreme trajectories ever recorded. It tells a story that spans billions of years and crosses a significant fraction of the galaxy. And if we learn to read it carefully, if we decode the numbers and trace the path backward through time, it reveals secrets about the architecture of the Milky Way that we're only beginning to understand. Let's start with the basics. An orbit is defined by 6 parameters, 6 numbers that completely specify the size, shape, orientation, and timing of an object's path through space. For 3IATLAS, the most striking parameter is eccentricity. Eccentricity measures how elongated an orbit is, how much it deviates from a perfect circle. A circular orbit has an eccentricity of 0. Earth's orbit around the Sun has an eccentricity of 0.07, nearly circular. Halley's Comet has an eccentricity of 0.967, a long stretched ellipse that takes it from the inner solar system out past Neptune and back again every 76 years. But 3IATLAS has an eccentricity of 6.1374, 6.1. That's not an ellipse, that's a hyperbola. It's the highest eccentricity ever measured for any confirmed interstellar object, higher than Oumuamua's 1.2, higher than Borisov's 3.36. An eccentricity greater than 1 means the orbit is unbound. The object is moving faster than escape velocity. It will never return. And an eccentricity of 6 means it's moving much faster than escape velocity. It's not just leaving, it's fleeing. When 3IATLAS reached perihelion on October 29, 2025, it was traveling at about 40 kilometers per second relative to the Sun. That's fast but not unprecedented. Many comets move that fast when they're close to the Sun, accelerated by the steep gravitational well near the star. But the key number is the hyperbolic excess velocity, the speed the object has relative to the Sun when it's far enough away that the Sun's gravity is negligible. For 3IATLAS, that velocity is 58 kilometers per second. 58. That's the baseline speed it had when it entered the solar system, and the speed it will have when it leaves. That's its intrinsic velocity relative to the Sun, the speed that tells you where it came from and how long it's been traveling. And 58 kilometers per second is fast. It's more than twice the speed most local stars orbit the galactic center. It's the kind of speed that accumulates over billions of years of falling through the galaxy's gravitational potential, picking up momentum, losing momentum, trading energy with every star and nebula you pass. But raw speed doesn't tell the whole story. Direction matters, orientation matters, and this is where things get really interesting. In astronomy, when we want to understand where something came from in the galaxy, we break down its velocity into 3 components using the galactic coordinate system. U is the radial velocity positive, moving away from the galactic center, negative moving toward it. V is the tangential velocity, positive in the direction of galactic rotation, negative against it. W is the vertical velocity positive, moving upward through the galactic plane toward the north galactic pole, negative moving downward toward the south. These 3 numbers, U, V, and W, define how an object is moving relative to the overall structure and motion of the galaxy. For 3IATLAS, U is negative 51 kilometers per second. That means it's moving away from the galactic center at 51 km/s relative to the Sun. V, the tangential component, is small and not particularly remarkable, but W, the vertical component, is positive 18.5 kilometers per second. 18.5. That's high. That's unusual. That's the number that tells us something profound about where this comet came from. Most stars in the solar neighborhood, stars like the Sun, have vertical velocities of only a few kilometers per second. They bob up and down through the galactic plane as they orbit, but they don't venture far. They stay within the thin disk, the flattened structure where most of the galaxy's mass and star formation activity is concentrated. The thin disk is typically about 1,000 light-years thick, and stars within it oscillate gently, crossing the mid-plane every few tens of millions of years, but never straying too far above or below. A vertical velocity of 18.5 km/s is not gentle. That's not a star or a comet that's confined to the thin disk. That's something on a highly inclined orbit, something that travels far above and below the plane, something that belongs to a different population. The thick disk. The thick disk is harder to define, precisely because it blends into the thin disk and the stellar halo. But it's generally understood to be a population of older stars, with scale heights of 1 to 3,000 light-years stars that formed early in the galaxy's history, when the Milky Way was more turbulent, more chaotic, less settled into the orderly rotation we see today. Thick disk stars have higher random velocities, less organized motion, more eccentric and inclined orbits. And 3IATLAS, with its vertical velocity of 18.5 km/s, fits that profile perfectly. There's a common misconception that needs addressing here. When we say 3IATLAS came from the thick disk, people sometimes imagine it traveled all the way from some distant part of the galaxy, crossing tens of thousands of light years to reach us. That's not quite right. The thick disk isn't a specific location. It's a population, a category of objects defined by their orbital characteristics and ages. Thick disk stars are everywhere in the galaxy, including near the sun. They're just less common than thin disk stars, and they're moving differently on different trajectories. What makes 3IATLAS a thick disk object isn't that it came from far away, but that its orbit, its velocity structure, matches the kinematic signature of thick disk populations. It's moving like an old star would move on a path that takes it high above the galactic plane that crosses the thin disk at a steep angle that's not aligned with the organized rotation of younger stellar populations. And if it's moving like a thick disk star, it probably formed in the same era as thick disk stars, 8 to 12 billion years ago, when the galaxy was younger and the conditions were different. The inclination of the orbit relative to the ecliptic, the plane of Earth's orbit, is another striking number, 175.11 degrees. That's retrograde. It means 3IATLAS is moving opposite to the direction that planets orbit the sun. Most comets in our solar system are prograde, orbiting in the same direction as the planets, because they formed from the same rotating disk of material. A few are retrograde, usually long-period comets from the Oort cloud that have been perturbed into random orientations by passing stars. But an inclination of 175 degrees means 3IATLAS is nearly perfectly retrograde, almost exactly opposite to the planetary motion. That's not random. That's not a coincidence. That's the signature of something that arrived from a direction aligned with the galactic structure, cutting across the solar system's motion through the galaxy. When we trace the path backward, projecting where 3IATLAS came from before it entered the sphere of the sun's influence, it points towards Sagittarius, toward the galactic center rising upward from the galactic plane. It's as if the comet was climbing up through the disk, passing through our neighborhood, on its way to the galactic halo above, and we happen to be there at the right moment to see it. This trajectory, this specific combination of speed and direction and inclination, is incredibly rare. We've observed hundreds of thousands of comets and asteroids in the solar system, and none of them move like this. Oumuamua and Borisov, the two previous interstellar visitors, had hyperbolic orbits, but their trajectories suggested origins in the thin disk from stellar systems more like our own. 3IATLAS is different. Its path cuts deeper into galactic history, and the more we analyze that path, the more constraints we can place on where it must have come from and how old it must be. If you plug the velocity components into dynamical models of the Milky Way, if you simulate backward in time to see what kinds of orbits produce those specific numbers, you consistently get thick disk origins. Thin disk orbits don't work. Halo orbits don't work. Only thick disk orbits, the orbits of ancient stars from the galaxy's early epochs, match the data, and thick disk stars are old. The youngest thick disk stars are about 8 billion years old, The oldest might be 12 or 13 billion formed when the Milky Way was still assembling, when the disk was thicker and more turbulent, when star formation rates were higher, and the galaxy was richer in gas and poorer in metals. There's a beautiful symmetry to this. The comet's trajectory through our solar system, the path it follows as it swings past the sun and back out into the dark, is a microcosm of its trajectory through the galaxy. Just as it's passing through the solar system on a hyperbolic path never to return, it's been passing through different regions of the Milky Way on a galactic hyperbolic, wandering from neighborhood to neighborhood, encountering different stars, different densities of gas and dust, different radiation environments slowly mixing through the galaxy structure over billions of years. It left its parent star system long ago, ejected by some dynamical process. We can only guess at a close encounter with a giant planet, a stellar flyby that perturbed the Oort cloud equivalent of its home system, a supernova that disrupted the entire system and flung its comets into the interstellar void. Once ejected, it became a free agent subject, only to the collective gravity of the galaxy itself, orbiting the galactic center on a lonely tilted path that brought it eventually improbably to us. The close approaches to solar system planets during its passage are worth noting, not because they posed any danger, but because they help us refine the trajectory and understand the dynamics. On October 3, 2025, 3IATLAS passed within 0.19 astronomical units of Mars. That's about 18 million miles, close enough that Mars's gravity gave the comet a tiny nudge, a small change in velocity, that altered the subsequent path by a minuscule but measurable amount. On November 3rd, it passed 0.65 AU from Venus. On December 19th, it reached its closest approach to Earth at 1.8 AU, still far outside the Moon's orbit. No threat, just a passing visitor we could observe with moderate telescopes. And on March 16th, 2026, as it exits the inner solar system, it will pass 0.36 AU from Jupiter, roughly the distance from the Sun to Mercury, close enough for Jupiter's immense gravity to give it another small kick, adding a bit more energy, helping it on its way out. These planetary encounters are opportunities. Each one gives us another data point, another measurement of position and velocity, another chance to refine our understanding of the orbit. And because the encounters are gravitational, purely Newtonian, we can model them precisely and subtract their effects, allowing us to reconstruct the comet's original trajectory before it entered the solar system, the path it was on when it was still in interstellar space, still carrying the full imprint of its galactic journey. Have you ever tried to imagine traveling for 8 billion years? It's hard. Human brains aren't built to grasp timescales like that. 8 billion years ago, the Earth didn't exist. The Sun didn't exist. The cloud of gas and dust that would eventually collapse to form them was still scattered across a much larger volume, mingled with the remnants of older stars enriched by supernovae that had already exploded and faded. If 3IATLAS was already a comet, then already a frozen chunk of ice and rock orbiting some ancient star, it has been traveling through space for longer than our entire lineage from star to planets to life to consciousness has existed. It has outlasted stars. It has outlasted civilizations of stars, entire stellar populations that were born, lived, and died while it drifted through the dark. And yet, here it is still intact, still coherent, still recognizable as a comet, as if time itself has been gentler to it than to the countless worlds and suns that came and went during its journey. The path also tells us something about what 3IATLAS didn't encounter. It didn't pass through any dense molecular clouds, the stellar nurseries where new stars form. If it had the drag from gas and dust would have slowed it down, altered its trajectory, maybe even caused it to be recaptured by a new stellar system. It didn't pass too close to any supernova remnants, expanding shells of hot gas that would have heated it, stripped away its outer layers, destroyed its volatile ices. It didn't fall into a black hole or get torn apart by tidal forces near a neutron star. It navigated the galaxy's dangers either by luck or by traveling through regions that were relatively empty, relatively safe, the low-density expanses between spiral arms, the quieter neighborhoods of the thick disk, where stars are sparsely scattered, and the hazards are fewer. This survival is part of what makes it valuable. It's not just old, it's pristine, or as close to pristine as something that's been exposed to cosmic rays and micrometeorites for billions of years can be. It's a sample that hasn't been cooked, hasn't been crushed, hasn't been chemically altered beyond recognition. It's a direct snapshot of conditions in the ancient galaxy, frozen in time, delivered to our doorstep. The study by Yiyang Guo that identified 25 stars 3IATLAS may have passed within a parsec of in the last 10 million years is fascinating for what it reveals about the density of the galactic environment. A parsec is 3.26 light years, about 200,000 times the distance from Earth to the Sun. That sounds like a lot, but on galactic scales it's close. Close enough for gravitational perturbations. Close enough that if any of those stars had planetary systems with their own Oort clouds, 3IATLAS could have felt them, could have had its trajectory shifted slightly by the combined mass of star and orbiting material. 25 such encounters in 10 million years. That's an average of one close pass every 400,000 years. Scale that up to 8 billion years and you get 20,000 encounters. 20,000 opportunities for the orbit to change, for velocity to be added or subtracted, for the path to be bent in a new direction. Each encounter erases a little more of the historical record, makes it harder to trace backward, harder to identify the original parent star. After 20,000 perturbations, the connection to the origin is essentially lost. We can't point to a specific star and say that's where it came from. We can only say it came from a population of stars, with certain properties stars, that formed at a certain time, stars that occupy a certain dynamical niche in the galaxy. The thick disk, the ancient reservoir. There's a poetic irony here. The very thing that makes 3IATLAS so interesting, its age, its long journey through the galaxy, is also what makes it impossible to trace back to a specific home. If it were younger, if it had only been traveling for a few 100 million years, we might be able to identify candidate parent stars, narrow down the origin to a specific region of space. But because it's so old, because it's been mixing through the galaxy for so long, the trail has gone cold. We know where it came from, in a general sense, but not in a specific one. It's like finding an ancient artifact with no inscription, no context, no clear provenance, and trying to deduce its origin from the material it's made of and the style of its construction. You can make educated guesses, you can place it within a broader cultural and temporal framework, but you can't say exactly whose hands shaped it or exactly where it was made. 3IATLAS is a galactic artifact, and we're archaeologists trying to read its story from the fragments that remain. The trajectory also has implications for future observations. We now know 3IATLAS will remain observable until late January 2026, fading slowly as it moves away from the Sun and Earth, its coma dimming as the solar heating decreases and the sublimation slows. By February, it will be too faint for most ground-based telescopes, dropping below the threshold where useful spectroscopy can be done. But space-based instruments like Hubble and Webb might be able to track it a bit longer, capturing final measurements as it crosses the orbital distance of Mars, then Jupiter, then drifting into the outer solar system, where the cold returns and the comet goes dormant, the gases freezing back into ice, the jets shutting down the coma, collapsing into nothingness. Within a few years, it will cross the heliopause, the boundary where the sun's influence ends and interstellar space begins. And then it will be gone back into the deep dark, continuing its orbit around the galaxy, a billion-year ellipse that will carry it through the disk, up into the halo, back down through the disk, again endlessly cycling, endlessly wandering, until perhaps billions of years from now, it passes through another solar system and gives other beings the same opportunity to study it, to wonder at it, to marvel at its persistence. Tracing the future is easier than tracing the past, because we know the orbit precisely now. We've measured it from hundreds of observations, and we can integrate forward through time with high confidence. In 100,000 years, 3IATLAS will be several light years away, far beyond the reach of our solar system's gravity, moving through the local interstellar medium at 58 km/s. In 10 million years, it might pass near one of the stars Guo identified, or a different star entirely, and receive another gravitational nudge, another small change in trajectory. In 1 billion years, it will have completed another orbit around the galactic center, returning to roughly the same galactic radius, but displaced vertically, passing through a different height above the plane, encountering a different set of stars and nebulae. The galaxy itself will have changed by then. New stars will have formed. Old stars will have died. Spiral arms will have rotated to new positions. And 3IATLAS will still be there, still traveling, still carrying its ancient ice, still a fragment of the galaxy's deep past, moving through the galaxy's present. This is what orbits teach us. They teach us that motion is memory. Every object in space carries a record of where it's been encoded in how it's moving. Velocity is history. Trajectory is story. And when we learn to read those stories, when we develop the tools and the models and the understanding to decode the motion and extract the meaning, we gain access to information that would otherwise be lost. We can't go back in time. We can't visit the ancient galaxy directly. But we can study the things that survived from that era, the things that traveled forward through time to reach us. And 3IATLAS, with its steep path through the disk, its high vertical velocity, its retrograde inclination, is one of the clearest, most legible messages we've ever received from the galaxy's past. The mathematics of orbits is the language of cosmic history, and we're learning to read it fluently. Now the numbers begin to reveal not just where the comet has been, but when it began its journey and what that ancient beginning looked like in a galaxy that had not yet learned to make a sun like ours. Age is a strange thing when you're talking about objects in space. A tree, you can count its rings. A rock on Earth, you can measure the decay of radioactive isotopes trapped in its crystals. A star, you can estimate from its color, its brightness, the elements in its spectrum. But a comet that came from another star system that's been drifting through the galaxy for billions of years, with no connection to its parent, no way to sample it directly, no isotopes we can measure from 300 million miles away. That requires something different. That requires inference, statistics, models built on populations and probabilities. And yet, despite the uncertainty, despite the limitations, we can say with reasonable confidence that 3IATLAS is somewhere between 7 and 14 billion years old. Maybe older, maybe the oldest thing with a solid surface we've ever laid eyes on. How do we know this? How do we measure age across such unfathomable distances and timescales? Let's walk through it slowly, carefully, the way you'd trace a timeline backward through history, each step revealing another layer of the past. The first thing to understand is that we're not measuring the age of 3IATLAS directly. We can't. We don't have a sample we can bring into a lab. We can't drill into its nucleus and extract a core, can't analyze the isotopic ratios of oxygen or carbon or nitrogen locked in the ice. What we're measuring is the age of the stellar population it came from. We're looking at where it's moving, how it's moving, what that motion tells us about where it formed, and then using what we know about stellar evolution and galactic history to estimate when stars in that region typically formed. It's indirect, but it's robust. It's the same method astronomers use to estimate the ages of stars we can't study in detail. Stars too distant or too faint for direct spectroscopy. We look at their kinematics, their dynamics, their place in the galaxy structure, and we infer age from context. 3IATLAS's context is the thick disk, and the thick disk is ancient. Matthew Hopkins and his colleagues at Oxford used a statistical framework they had been developing for years, the the Otaudahai-Oxford model, to estimate the probability distribution of 3I-ATLAS's age. The model works by simulating millions of hypothetical interstellar objects, assigning them different ages, different parent star populations, different ejection velocities, and then integrating their orbits forward through a realistic model of the Milky Way's gravitational potential. Some of these simulated objects end up with velocity components similar to what we observe for 3I-ATLAS. Some don't. By comparing the ones that match to the ones that don't, by looking at what ages and populations produce the best fits to the observed data, Hopkins' team could calculate the likelihood that 3I-ATLAS came from different stellar populations. And the result was striking. 68% confidence that it originated from the thick disk. And if it came from the thick disk based on what we know about when thick disk stars formed, it's likely between 7.6 and 14 billion years old. That's the range where 2/3 of the probability mass lies. It could be younger, maybe as young as 3 billion years if you extend to lower confidence intervals, but that's less likely. The data favors old, very old. An independent analysis by Astor Taylor and Daryl Seligman came to similar conclusions. Using different methods, different assumptions, they estimated an age range of 3 to 11 billion years, with the most probable values clustering around 7 to 9 billion. The fact that two independent teams using different approaches got overlapping results is reassuring. It suggests the conclusion is robust, not an artifact of one particular model or set of assumptions. When different methods converge on the same answer, when the ranges overlap, and the central estimates agree, you start to feel confident that you're seeing something real, not just noise in the data or bias in the analysis. 3I-ATLAS is old, probably older than the solar system, possibly much older. Let's put those numbers in context. The universe itself is 13.8 billion years old, measured from the cosmic microwave background radiation, the afterglow of the Big Bang. That's the absolute upper limit. Nothing can be older than the universe. The first stars, the so-called population 3 stars, made entirely of hydrogen and helium, with no heavier elements, formed a few 100 million years after the Big Bang, around 13.5 billion years ago. Those stars were massive and short-lived, burning through their fuel in a few million years, exploding as supernovae and scattering the first heavy elements into the cosmos. The second generation of stars, population 2, stars with trace amounts of metals formed from that enriched gas, and many of them are still around today. Ancient red dwarfs and subdwarfs orbiting in the galactic halo and thick disk. Our Sun is a population 1 star, relatively young at 4.6 billion years, formed from gas that had been enriched by many generations of previous stars. If 3I-ATLAS is 12 or 13 billion years old, it formed during the population 2 era, when the galaxy was still assembling, when star formation was at its peak, when the Milky Way looked nothing like it does now. That epoch from about 10 to 13 billion years ago is sometimes called cosmic noon. It's the period when the universe's star formation rate was at its maximum, when galaxies were colliding and merging and lighting up with newborn stars at a pace that will never be matched again. The galaxies from that era, the ones we can observe at high redshift, with telescopes like Webb, look chaotic, turbulent, full of dense clumps of gas collapsing into star clusters, full of supernovae and stellar winds and feedback processes that are shaping the next generation. The Milky Way went through that phase, and somewhere in the midst of that chaos around a star, we'll never identify in a protoplanetary disk made of gas and dust that had been through only a few cycles of stellar enrichment 3I-ATLAS formed. A comet. A small cold ball of ice and rock, one of perhaps billions or trillions of similar objects orbiting that ancient star, most of which were eventually destroyed or ejected or accreted onto planets that may or may not still exist. 3I-ATLAS is the survivor, The one that escaped the one that made it through billions of years of galactic wandering to arrive here now in our telescopes. 14 billion years. Try to imagine that span. The Earth is 4.54 billion years old, dated from meteorites and the oldest rocks we can find. The Moon is slightly younger, about 4.51 billion, formed when a Mars-sized object collided with the early Earth, and the debris coalesced into our satellite. The oldest known rocks on Earth's surface are the Acasta gneiss in Canada, about 4 billion years old, metamorphosed and deformed, but still preserving a record of the planet's violent youth. The oldest minerals, tiny zircon crystals found in Western Australia, are 4.4 billion years old, formed when the Earth's crust was just beginning to solidify, when the surface was still molten, in places when the oceans were just condensing from steam. If 3IATLAS is 12 billion years old, it predates all of that by 7.5 billion years. It predates the Earth by a factor of nearly 3. It was already ancient, already drifting through the galaxy, already carrying its cargo of frozen volatiles when the cloud of gas and dust that would become our solar system was still scattered across hundreds of light years, not yet collapsed, not yet aware of its destiny. There's a common mistake people make when thinking about ages this vast. They imagine time as a linear progression, a straight line from past to present, with events spaced evenly along it. But cosmic time doesn't work that way. The universe's history is front-loaded. Most of the important events, most of the structure formation, most of the star formation happened early. The first few billion years saw the formation of galaxies, the first heavy elements, the first planets, the first conditions that could support something like life. By the time our solar system formed 4.6 billion years ago, the universe was already 2/3 of its current age. It was mature, settled. The wild early days were over. So, when we say 3IATLAS might be 12 billion years old, we're not just saying it's old, we're saying it's from the early days. It's from the epoch when the rules were different, when the galaxy was still being shaped by forces that no longer dominate when the chemistry was different, because fewer generations of stars had lived and died. And that chemistry matters. Stars are the factories that make elements heavier than hydrogen and helium. In their cores, they fuse lighter elements into heavier ones, turning hydrogen into helium, helium into carbon and oxygen carbon, into neon and magnesium, all the way up to iron. When massive stars explode as supernovae, they produce even heavier elements, the gold and silver and uranium, and scatter all of it into space, enriching the interstellar medium. Each generation of stars that forms from that enriched gas has a higher fraction of heavy elements, higher metallicity than the generation before. Astronomers measure this using the ratio of iron to hydrogen expressed on a logarithmic scale relative to the Sun. The Sun has a metallicity of 0 by definition. Stars with less iron than the Sun have negative metallicity. Stars with more have positive metallicity. Thick disk stars typically have metallicities between -1 and -0.5, meaning they have 10% to 30% as much iron as the Sun. That's because they formed earlier from gas that had been through fewer cycles of enrichment. And if 3IATLAS formed around a thick disk star, it should reflect that lower metallicity in its composition. This is harder to test directly because we're not measuring the metallicity of the parent star. We're measuring the composition of the comet, and comets are made mostly of volatiles ices, not metals, but there are tracers, ratios of different isotopes, abundances of certain elements that are preferentially produced in specific types of supernovae. The nickel to iron ratio we mentioned earlier, which is higher in 3IATLAS than in solar system comets, could be a signature of this. Nickel and iron are both produced in supernovae, but in slightly different proportions depending on the mass of the progenitor star and the specific conditions of the explosion. If 3IATLAS formed from material processed through early supernovae from a different generation of stars, with different mass distributions, we'd expect the nickel to iron ratio to be different. And it is. It's subtle, but it's there. A chemical fingerprint pointing back to the ancient galaxy. Another piece of the puzzle comes from water. Early observations suggested that 3IATLAS is water-rich, producing large amounts of water vapor as it heats up near the sun. The Otau-Tahi-Oxford model predicted this. Hopkins and Lintott argued that thick disk comets should have more water ice than thin disk comets because they formed in colder environments farther from their parent stars, in systems where the snowline, the boundary beyond which water can condense into ice, was located at greater distances. The reasoning is based on metallicity. Lower metallicity stars produce less dust in their protoplanetary disks because there are fewer heavy elements to condense into solid grains. Less dust means less opacity, less absorption of stellar light, which means the disk stays colder at a given distance from the star. A colder disk means the snowline moves inward, closer to the star, which means more of the disk's material can form icy bodies like comets. It's a cascade of effects, one consequence leading to another, linking the metallicity of the parent star to the composition of the comets that form around it. And the water richness we're seeing in 3IATLAS is consistent with that prediction. It's an independent line of evidence separate from the kinematics that supports the thick disk origin in the ancient age. But let's be clear about the uncertainties. These age estimates are probabilistic, not deterministic. They're based on models, and models are only as good as the assumptions that go into them. The Otau-Tahi-Oxford model assumes certain things about how the galaxy's stellar populations are distributed, how comets are ejected from planetary systems, how velocities evolve over time as objects interact with the galactic potential and with passing stars. If any of those assumptions are wrong, the age estimate could be wrong too. The 68% confidence interval means there's a 1 in 3 chance the true age falls outside that range. It could be younger, it could be older. We're not claiming certainty. We're claiming the best estimate we can make, given the data we have and the tools we've developed. And those tools are good. They're based on decades of work on models that have been tested against known populations, on statistical methods that are designed to account for uncertainty. But they're not perfect. Science rarely is. There's also the question of what age even means for an object like this. When we say 3IATLAS is 12 billion years old, do we mean it formed 12 billion years ago? Or do we mean its parent star formed 12 billion years ago? And the comet formed later, maybe hundreds of millions of years later, once the protoplanetary disk had settled and planets had started to form. The distinction matters because the age of the star and the age of the comet aren't necessarily the same. In our solar system, the sun formed about 4,568 billion years ago, and the oldest meteorites, the calcium-aluminum-rich inclusions that condense from the solar nebula, are about 4,567 billion years old, only a million years younger. The gap is small. But in some systems, especially turbulent ones, where disk dispersal is slow or planet formation is delayed, the gap could be larger. So, when we estimate 3IATLAS's age at 8 to 12 billion years, we're really estimating the age of the stellar population it came from, with the understanding that the comet itself might be slightly younger, though not by much on cosmic timescales. 100 million years is a rounding error when you're talking about billions. Here's something that might help make this tangible. The oldest known star in the Milky Way that we've identified and studied in detail is called HD 15883, sometimes nicknamed the Methuselah star. It's a subgiant star about 190 light-years from Earth, and based on its metallicity and evolutionary state, it's estimated to be about 14.5 billion years old, give or take a billion years, depending on the uncertainties in the models. That's awkwardly close to the age of the universe, which has led to some interesting discussions about whether the age estimate for the star or the age estimate for the universe needs to be revised. But the key point is that stars that old exist. They're rare, mostly found in the halo and thick disk, but they're out there. And around some of those stars, presumably protoplanetary disks formed, and planets and comets formed from those disks. And some of those comets got ejected, and some of those ejected comets are still out there wandering the galaxy, waiting to pass through solar systems like ours, where beings might notice them and wonder. 3IATLAS might be one of those comets, a fragment from the era of Methuselah, stars from the galaxy's deep youth still carrying ice that condensed from vapor when the Milky Way was unrecognizable. There's a moment in every scientist's career when the scale of what they're studying hits them emotionally, not just intellectually. For Hopkins, that moment probably came when he ran the numbers and saw the age range come out to 8 to 12 billion years. For Lintott, it might have been when he said in an interview that this is an object from a part of the galaxy we've never seen up close before. For the astronomers observing it night after night, tracking its motion, measuring its spectra, it might come in quiet moments between observations looking up at the sky and thinking about the fact that the faint smudge in their telescope eyepiece has been traveling longer than continents have existed, longer than mountains have stood, longer than oceans have filled. We're looking at something that predates not just human history, but geological history, planetary history, stellar history. It's older than the story we tell ourselves about where we come from. And that's humbling. Does it change anything knowing this? Does it matter that 3IATLAS is ancient beyond imagining, rather than merely old? In practical terms, maybe not. The science we can do is the same whether it's 4 billion years old or 12. We can still measure its composition, track its orbit, study its activity. But in emotional terms, in philosophical terms, it matters. It shifts perspective. It reminds us that our solar system, our sun, our Earth are not the default. They're one instance in a vast population of stellar systems that spans cosmic time. Most of those systems are older than ours. Most of the stars that have ever formed in the galaxy formed billions of years before the sun ignited. And some of those stars had planets and comets and maybe even life, and most of it is gone now, recycled into new generations. The original structure's erased, but occasionally a fragment survives. A comet that escaped, that avoided recapture, that drifted alone for billions of years and ended up here giving us a glimpse, a fleeting contact with epochs we can normally only study through light, that's been traveling for billions of years, light from galaxies so distant, we're seeing them as they were in the early universe. 3IATLAS is that same deep past, but it's here, it's local, it's something we can study with the tools we have from the place where we are. The age also has implications for the search for life beyond Earth. If comets like 3IATLAS were delivering water and organic molecules to planets 8 or 10 or 12 billion years ago, if those planets were habitable, if life arose on them, then life in the galaxy could be much older than life on Earth. Earth's oldest confirmed fossils are about 3.5 billion years old, stromatolites and microbial mats that left traces in ancient rock. But life on Earth probably started earlier, maybe 4 billion years ago, shortly after the late heavy bombardment ended, and the surface became stable enough for complex chemistry to persist. That means life on Earth has had 4 billion years to evolve, to diversify, to produce everything from bacteria to redwood trees to human beings. Now, imagine a planet that formed 10 billion years ago around a thick disk star and received comets like 3IATLAS and developed life 9 billion years ago. That life would have had 9 billion years to evolve. What would 9 billion-year-old life look like? What could it become given that much time? We don't know. We can't know. But it's a staggering thought. And it's grounded in real science and the fact that stars older than the sun exist, that planets can form around those stars, that comets from those systems are passing through ours right now, carrying the chemical building blocks that life needs. Of course, we have no evidence that 3IATLAS carries life or even complex organics beyond the simple prebiotic molecules we've detected. This isn't panspermia. This isn't a claim that life on Earth came from space, though that hypothesis has its proponents and can't be completely ruled out. This is just the observation that the ingredients for life water in carbon and nitrogen and phosphorus have been present in the galaxy for much longer than they've been present in our solar system. And if the ingredients have been present, if habitable planets have been present, if time has been present, then life could have arisen elsewhere long before us in conditions we're only now beginning to understand. 3I/ATLAS is a data point in that larger story. A single comet can't prove anything about ancient life, but it can show us that the ancient galaxy was not so different from the modern galaxy, that the processes that make planets and comets and complex chemistry were operating then, as they are now, that the universe has been fertile for a very long time. Before we move on, before we turn our attention to the chemistry and the activity and the observations, sit with this number for a moment. 12 billion years. 12 billion trips around the sun. If you were counting days, though, of course, 3I/ATLAS hasn't orbited the sun, hasn't orbited anything since it left its parent star. 12 billion years of drifting, of silence, of cold and dark and nothing but the faint background glow of distant stars and the cosmic microwave background radiation. The fossil heat of the Big Bang, slowly redshifting, slowly cooling as the universe expands. And through all of that, this small object persisted, held together, remained intact. Waiting though, it doesn't know, it's waiting for a moment like this when it would pass close enough to a star that beings on a planet around that star would notice, would study, would care. We're witnessing something rare, something precious, a meeting between the ancient and the modern, between the galaxy's past and its present, mediated by ice and math, and the patient work of people who point telescopes at the sky and ask questions about what they see. The age of 3I/ATLAS is not just a number, it's a bridge, a connection between now and then, between here and there, between what we know and what we're still learning. And what we're learning increasingly is written not just in the trajectory, not just in the age, but in the molecules themselves, in the specific mixture of atoms that make up this ancient wanderer, a chemical archive waiting to be decoded. Every molecule tells a story. Every atom carries a history. When you break down the light from a comet into its component wavelengths, when you analyze the spectrum and identify the dark lines where specific elements have absorbed photons, when you measure the ratios and compare them to what you'd expect from solar system objects, you're not just doing chemistry, you're reading a letter, a message written in the language of atoms, sent from a place and time you can never visit, decoded through the patience of spectroscopy and the precision of quantum mechanics. The chemistry of 3I/ATLAS is strange, familiar enough to recognize as a comet, different enough to know it's not from here. And in those differences in the specific proportions of water and carbon dioxide and hydrogen cyanide, in the unusual abundance of nickel relative to iron, in the signature of ice that formed in extreme cold, far from any star, we're seeing something profound. We're seeing the periodic table as it existed in the ancient galaxy before our sun added its own contribution to the cosmic mix. Spectroscopy is one of the most powerful tools in astronomy. It works because every element, every molecule interacts with light in specific predictable ways. Electrons and atoms can only occupy certain energy levels, and when they jump between those levels, they either absorb or emit photons of very specific wavelengths. Hydrogen absorbs at 656 nanometers in the red part of the spectrum. Oxygen has strong lines in the ultraviolet. Sodium produces the familiar yellow doublet at 589 nanometers. These signatures are unique, like fingerprints, and they're the same everywhere in the universe because the laws of quantum mechanics are the same everywhere. When we point a spectrograph at 3I/ATLAS and spread its light into a rainbow, we see those fingerprints. We see the dark lines where molecules in the coma have absorbed sunlight. And from the pattern of those lines, from their depths and widths and positions, we can identify what the comet is made of, even from 300 million miles away. It's a kind of alchemy in reverse turning light back into matter, into knowledge, into understanding. The first and most abundant molecule detected in 3IATLAS is water vapor, H2O, 2 hydrogen atoms bonded to 1 oxygen. The most common solid in the outer regions of planetary systems, the substance that makes up most of Earth's oceans, the molecule that life as we know it depends on. Water is ubiquitous in comets because it's ubiquitous in protoplanetary disks. When a disk of gas and dust surrounds a young star, there's a boundary called the snow line, the distance from the star, where temperatures drop low enough for water to condense from vapor into ice. Inside the snow line, water stays gaseous, or gets incorporated into hydrated minerals. Outside the snow line, it freezes onto dust grains, forming icy particles that stick together and grow into comets and the cores of giant planets. In our solar system, the snow line was located somewhere between Mars and Jupiter, which is why the inner planets are rocky and dry, while the outer planets and their moons are rich in ice. 3IATLAS formed beyond the snow line of its parent star, in the cold outer reaches where water ice was stable. And it's been carrying that ice ever since frozen solid in the interstellar medium, where temperatures hover just a few degrees above absolute zero. As 3IATLAS approached the sun in the summer and fall of 2025, that ice began to sublimate. The sun's heat penetrated the surface, warming the outer layers, causing water molecules to break free from the crystal lattice and escape into space. This process sublimation is what makes comets visible. The escaping gas forms a glowing cloud around the nucleus, the coma, and carries dust particles along with it, creating the tail. Spectroscopic observations by multiple telescopes detected strong water absorption lines in the coma, confirming that water is the dominant volatile. Estimates suggest 3IATLAS is losing several hundred kilograms of water per second at its peak activity, a rate comparable to what we see in active comets from the Oort cloud at similar distances from the sun. That's a lot of water. Over the course of its passage through the inner solar system from July 2025 to January 2026, it will lose millions of tons of ice, a tiny fraction of its total mass, but enough to make it dramatically visible enough to give us the data we need to analyze its composition. But water alone doesn't tell us much. All comets have water. What makes 3IATLAS interesting is the other molecules, the trace species, the subtle differences in abundance that hint at a different origin. The second most abundant volatile detected is carbon dioxide, CO2. Like water, carbon dioxide is common in comets, but it's more volatile, meaning it sublimates at lower temperatures. In our solar system, CO2 ice can survive farther from the sun than water ice, and comets often show CO2 activity before water activity kicks in. Observations from the James Webb Space Telescope, which is sensitive to infrared wavelengths, where CO2 has strong absorption features, revealed unusually high levels of carbon dioxide in 3IATLAS's coma, higher than what we typically see in solar system comets. The ratio of CO2 to H2O is elevated, suggesting that 3IATLAS formed in an environment that was particularly rich in carbon dioxide, possibly a region of its protoplanetary disk that was colder than the equivalent region in our solar system, allowing more CO2 to condense onto grains and be incorporated into the growing comet. This makes sense if you think about the metallicity connection. Lower metallicity stars have less dust in their disks because there are fewer heavy elements to form dust grains. Less dust means the disk is more transparent to starlight, which means it stays colder at a given distance. A colder disk means the snow lines for different volatiles move inward closer to the star. Water's snow line moves in. Carbon dioxide's snow line moves in. Ammonia's snow line moves in. And the result is that comets forming in those disks incorporate more of these ices relative to rock and dust, because a larger fraction of the disk's mass is in the form of condensed volatiles. The elevated CO2 to H2O ratio in 3IATLAS is consistent with formation around a metal-poor star, a thick disk star, exactly what we'd expect if the age estimates are correct. It's an independent line of chemical evidence supporting the kinematic and statistical arguments for an ancient origin. The third key molecule is hydrogen cyanide HCN. This is where things get really interesting. Hydrogen cyanide is a prebiotic molecule, one of the building blocks of more complex organic chemistry. It's toxic in high concentrations, but in the right conditions, it can polymerize to form adenine, one of the nucleotide bases in DNA and RNA. It's found in the interstellar medium in the atmospheres of planets like Titan and in the comae of comets. It's not unusual to find HCN in a comet. What's unusual is how much of it 3IATLAS is producing. Observations by the James Clerk Maxwell Telescope in Hawaii, using radio wavelengths to detect the rotational transitions of HCN molecules, measured a production rate of about 1.5 times 1025 molecules per second in early September 2025. That's roughly 2.5 kilograms per second. By mid-September, the rate had increased to 4.5 times 1025 molecules per second, about 4.5 kilograms per second. These are high rates higher than most solar system comets show, at comparable distances from the Sun. It suggests that 3IATLAS's nucleus is rich in HCN ice, or in parent molecules that break down into HCN when they're heated, and that the interior is still pristine, still loaded with volatiles that haven't been depleted by billions of years of slow sublimation in interstellar space. How is that possible? If 3IATLAS is really 12 billion years old, if it's been drifting through the galaxy for all that time, shouldn't it be a dead rock by now? All the ice long since evaporated. This is one of the puzzles. Interstellar space is cold, typically about 3 degrees Kelvin, just above absolute zero. At those temperatures, sublimation is incredibly slow, almost negligible. But it's not zero. Over billions of years, even slow sublimation adds up. And there are other factors. Cosmic rays' high-energy particles that permeate the galaxy can penetrate the surface of a comet and break chemical bonds, releasing gas even without heat. Micrometeorite impacts can chip away at the surface, exposing fresh ice underneath. Close passes by stars can warm the comet temporarily, causing brief episodes of activity. All of these processes should gradually erode the volatile content, turning a fresh comet into an inert, depleted object over time scales of a few billion years. And yet, 3IATLAS is vigorously active producing gas at rates that suggest a relatively fresh interior. Either our models of cometary aging are incomplete, or 3IATLAS has spent most of its existence in extremely stable, extremely cold regions of the galaxy, where the erosion rate was minimal. Perhaps it spent billions of years in the thick disk's outskirts, far from any stars, far from dense molecular clouds, just drifting in the void where nothing could touch it, nothing could warm it, nothing could strip away its ice. There's also the possibility that the comet has an insulating crust. Many comets develop a thin layer of non-volatile material on their surface, a lag deposit of dust and rocky grains left behind as the ice sublimates. This crust can insulate the interior, slowing the loss of volatiles, allowing the comet to remain active over longer time scales than you'd expect for a bare ice ball. If 3IATLAS developed such a crust early in its journey, perhaps during its last passage near a star, before it was ejected from its parent system, that crust could have protected the interior for billions of years, preserving the ice, keeping the comet fresh. And now, as the sun heats the surface, as the crust cracks and fractures and allows gas to escape, we're seeing the release of materials that have been locked away since the comet formed pristine samples of the ancient protoplanetary disk time capsules of chemistry that predates our solar system. The metal content is another clue. spectroscopic observations detected emission lines from neutral atoms of iron and nickel in the coma. These aren't gases. Iron and nickel don't sublimate at cometary temperatures. What we're seeing are atoms that have been sputtered off dust grains in the coma, released when ultraviolet light from the sun breaks molecular bonds, or when collisions between grains liberate individual atoms. The presence of these metals is normal. Most comets show iron and nickel emissions. What's abnormal is the ratio. In solar system comets, the abundance of iron relative to nickel is typically about 10-1. Iron is more common because it's produced more efficiently in supernovae, especially in Type II supernovae, the explosions of massive stars. Nickel is rarer, produced primarily in Type Ia supernovae, the thermonuclear detonations of white dwarf stars. The balance between these two types of supernovae, and thus the ratio of iron to nickel scattered into the interstellar medium, has changed over the galaxy's history as the stellar population evolved. Early in the galaxy, when most stars were massive and short-lived, Type II supernovae dominated, producing lots of iron. Later, as the population aged and more white dwarfs formed, Type Ia supernovae became more common, adding more nickel to the mix. If 3IATLAS formed in the early galaxy from material processed through fewer generations of supernovae, the iron-to-nickel ratio should be higher than what we see in solar system objects. And intriguingly, the observation suggests the opposite. The nickel emission is stronger than expected relative to iron, giving a lower iron-to-nickel ratio. This is a bit puzzling, and it highlights the limits of what we can infer from these observations. One possibility is that the dust grains in 3IATLAS are enriched in nickel for reasons unrelated to supernova nucleosynthesis, perhaps because the specific conditions in its parent disk favored the condensation of nickel-bearing minerals. Another possibility is that our understanding of how iron and nickel are released from dust grains and how they emit light in cometary comae is incomplete, and the ratio we measure spectroscopically doesn't directly reflect the ratio in the solid material. Or it could be a genuine signature of the ancient galaxy, a clue that the early supernovae that enriched 3IATLAS's parent cloud had different properties than the supernovae we study in the local universe today. We don't know yet. This is the frontier. This is where the data meets the edge of our models and says, here's something you need to figure out. Sulfur is another element to watch. Sulfur compounds are common in comets, and the ratio of sulfur to oxygen can tell you about the temperature and chemistry of the disk where the comet formed. Unfortunately, sulfur is hard to detect from the ground because Earth's atmosphere absorbs many of the wavelengths where sulfur compounds have strong features. Hubble attempted ultraviolet spectroscopy of 3IATLAS in November 2025, targeting sulfur emissions, but the results haven't been fully analyzed yet. If the sulfur to oxygen ratio is unusual, if it's higher or lower than what we see in solar system comets, that would be another piece of the puzzle, another constraint on the formation environment. Scientists are waiting for that data the way archaeologists wait for radiocarbon dates on a newly excavated artifact. Every measurement narrows, the possibilities refines. The picture brings us closer to understanding. And then there's the isotopic composition. Isotopes are versions of an element with different numbers of neutrons in the nucleus. Carbon-12 and carbon-13 are both carbon, but carbon-13 has one extra neutron. The ratio of carbon-13 to carbon-12, written as 13Cc12C, can tell you about the environment where the carbon atoms formed and the processes they've been through. In our solar system, the 13C12C ratio varies slightly between different objects depending on where they formed and what chemical reactions they underwent, but it's generally close to the ratio. We see in the Sun about 1 part in 90. If 3IATLAS has a significantly different 13C12C ratio, that would be strong evidence of a different origin, a different stellar environment. The same goes for oxygen isotopes, nitrogen isotopes, sulfur isotopes. Unfortunately, measuring isotopic ratios in a comet from 300 million miles away is incredibly difficult. It requires high-resolution spectroscopy and long integration times, and even then the signal is often too weak to give reliable results. Astronomers are trying. Multiple observing teams have submitted proposals to use the most sensitive spectrographs on the largest telescopes to target 3IATLAS and search for isotopic signatures. But it's a race against time because the comet is fading, moving farther from the sun, producing less gas, becoming harder to observe. We might get the data. We might not. Either way, the attempt is worth it. Because if we succeed, if we can measure the isotopes, it will be one of the most direct tests of the ancient origin hypothesis. Think about what it means to do chemistry at this scale across these distances. You're analyzing the composition of an object you can't touch, can't sample, can't bring into a laboratory. You're relying on the fact that atoms and molecules interact with light in predictable ways, that the spectrum carries information encoded in the positions and strengths of absorption and emission lines. You're building instruments sensitive enough to detect individual molecular transitions, telescopes large enough to collect enough photons to see faint features, models, sophisticated enough to interpret what the spectrum means in terms of temperature and density and composition. And you're doing all of this on an object that's only visible for a few months, that's moving, that's changing as it heats up and cools down, that's surrounded by a cloud of dust that scatters light and complicates the measurement. It's astonishingly hard. And yet, we can do it. We have done it. The spectra exist. The data are being analyzed. And slowly, carefully, the chemical portrait of 3IATLAS is coming into focus. There's a common misconception that needs correcting. Some people hear that 3IATLAS is from another star system and assume it must be made of completely alien materials, exotic compounds we've never seen, chemistry that doesn't exist in our solar system. That's not how it works. The laws of chemistry are universal. The elements are the same everywhere because they're produced in stars and supernovae, and those processes are the same everywhere. What differs is the proportions, the ratios, the specific mix of hydrogen and helium and carbon and oxygen and all the heavier elements that go into making a comet or a planet or a star. A thick disk comet isn't alien. It's just old. It's made of the same stuff we're made of, but the recipe is slightly different because the ingredients available when it formed were in different proportions than they were when our solar system formed. It's like comparing bread baked in the 19th century to bread baked today. The basic ingredients are the same: flour and water and yeast, but the specific types of wheat, the quality of the water, the strains of yeast might be different, and those differences affect the texture and flavor of the final product. 3IATLAS is ancient bread, baked from an older recipe in an oven we'll never see. The chemistry also tells us about processes, about how ices form and evolve, about how molecules survive in interstellar space, about what happens when a comet is heated after billions of years of cold storage. Every observation is a test of our theories, a chance to see if the models we've built to describe cometary behavior hold up when applied to an object from a completely different context. So far, mostly they do. 3IATLAS behaves like a comet. It sublimates. It produces a coma. It develops a tail. The molecules we detect are familiar, but the details, the ratios, the abundances are subtly off. And those subtleties are where the science lives, where the new knowledge is hiding, where the ancient galaxy is speaking to us if we listen carefully. Before we move on, before we turn to the activity and the jets and the physical structure, pause and appreciate what spectroscopy gives us. It gives us composition without contact. It gives us chemistry without sampling. It gives us knowledge across distances so vast that light takes hundreds of millions of years to traverse them. It's not perfect. It's not complete. But it's miraculous in its own way, this ability to break light into colors and read stories written in wavelengths, to decode the chemical signature of an object, that formed when the galaxy was young, that survived the chaos of billions of years, that arrived at our doorstep, just when we had the tools to study it. The spectrum of 3IATLAS is a text, and we're still learning to read it fluently. But every line we translate, every molecule we identify, every ratio we measure, brings us closer to understanding not just this one comet, but the history of matter itself. The journey of atoms from the Big Bang, through generations of stars, to the icy bodies that wander between them, carrying messages we're only now learning to receive. Chemistry is memory. And 3IATLAS remembers things. We've forgotten things that happened before we existed, things written in the proportions of ice and metal, and the faint glow of molecules caught in sunlight. But chemistry alone is static, a snapshot. To see the comet truly alive, to watch it respond to the sun's warmth, to witness the ancient ice awakening after billions of years, we need to observe not just what it's made of, but how it moves, how it changes, how it breathes. A comet is never truly still. Even when it looks like a fixed point in the sky, a steady smudge through a telescope, it's churning inside. Ice is sublimating. Gas is escaping. Dust is being lifted and carried away. The nucleus is rotating, tumbling through space, presenting different faces to the sun. At different times, each face with its own history of impacts and erosion and geological processes we barely understand. And when that comet is as old as 3IATLAS, when it's been frozen for billions of years, and is suddenly warmed by a star it's never encountered before, the awakening is spectacular. Jets erupt from the surface. The coma expands and contracts. The tail grows and shifts and sometimes splits into multiple streams. Every moment is dynamic. Every observation captures a comet in the act of transformation. And if you watch carefully, if you track those jets night after night, if you measure how they change and where they point, and how bright they get, you can decode the rotation of the nucleus map, the active regions on its surface, and glimpse the internal structure of an object that has survived longer than worlds. Activity in comets is driven by sublimation, the direct transition of ice from solid to gas without passing through a liquid phase. This happens because the pressure at a comet's surface is effectively zero. There's no atmosphere to speak of, just the faint wisps of gas that escape and immediately disperse into space. When sunlight heats the surface, when the temperature rises above the sublimation point for a particular ice, molecules break free from the crystal lattice and stream outward, carrying momentum, carrying energy, creating pressure that can lift dust grains and rocky particles along with them. Water ice sublimates at temperatures around 200 Kelvin, about minus 100 degrees Fahrenheit. Carbon dioxide sublimates at even lower temperatures around 150 Kelvin. And the more volatile species, things like carbon monoxide and methane, can sublimate at temperatures well below 100 Kelvin. As a comet approaches the sun, as different parts of its surface warm to different temperatures, different ices activate at different times, creating a complex pattern of outgassing that depends on the composition, the structure, and the rotation of the nucleus. 3IATLAS began showing activity much earlier than most comets. It was already producing a detectable coma when it was discovered in July 2025 at a distance of 4.5 astronomical units from the Sun, well beyond the orbit of Mars. At that distance, water ice is still mostly stable, not warm enough to sublimate rapidly. But carbon dioxide isn't. And if the nucleus has pockets of CO2 ice near the surface, or if there are cavities where CO2 gas has been trapped under a thin crust, that gas can escape even at large distances, creating early activity. This is what we saw. The first images from ATLAS and follow-up telescopes showed a faint, fuzzy coma surrounding the nucleus, expanding slowly diffuse, not yet structured. As the comet moved closer to the sun through August and September, the activity increased, the coma brightened, the outgassing rate went up, and by late September, when 3IATLAS was about 2.3 AU from the sun, detailed observations began to reveal something unusual. The coma wasn't uniform, it had structure. There were jets. Jets are collimated streams of gas and dust erupting from specific points on the nucleus. They look like spokes or fans extending from the central condensation, brighter than the surrounding coma, sharply defined, sometimes curved, sometimes straight. Jets form when active regions on the surface areas where fresh ice is exposed, or where subsurface pockets of gas are venting, produce more outgassing than the surrounding terrain. The gas flows outward accelerated by the pressure gradient, and if the flow is fast enough and concentrated enough, it stays collimated for hundreds or thousands of kilometers before dispersing into the general coma. The direction a jet points depends on where the active region is located on the nucleus and what direction the surface normal is pointing when the sun illuminates it. As the nucleus rotates as different regions come into sunlight and go into shadow, jets turn on and off, shift position, change brightness. Tracking jets over time is one of the best ways to determine the rotation period and orientation of a comet's spin axis. Astronomers at the 3IATLAS Observatory in Tenerife, using the 2-meter twin telescope, began a monitoring campaign in late August, observing 3IATLAS night after night, capturing images of the coma and analyzing the structure of the jets. Over 37 consecutive nights, they recorded how the jets evolved, how their positions shifted, how their brightness changed. And a pattern emerged. The jets weren't random. They weren't chaotic. They showed a regular periodic behavior wobbling back and forth with a cycle time of about 15.5 hours. That's the rotation period of the nucleus, the time it takes for the comet to complete one full spin. 15.5 hours, longer than Earth's rotation, shorter than Mars's. A slow, steady tumble through space like a wheel turning underwater, graceful and deliberate. But there was more. The jets didn't just rotate with the nucleus, they precessed. Precession is a slow wobble of the rotation axis itself, like the way a spinning top wobbles as it slows down, tracing out a cone in space. For 3IATLAS, the precession period was about 7 hours and 45 minutes, exactly half the rotation period. This is a telltale signature of a specific type of rotation called a torque-free precession, which happens when the nucleus isn't a perfect sphere, when it has an irregular shape with different moments of inertia along different axes. Imagine a potato spinning in space. If you give it a twist and let it go, it doesn't just spin smoothly around one axis. It tumbles, rotating around its long axis while that axis itself wobbles. That's what's happening with 3IATLAS. The nucleus is elongated, probably a contact binary or a highly irregular rubble pile, and it's spinning in a complex mode that combines rotation and precession. The jets erupting from fixed points on the surface trace out this motion, wobbling and shifting as the nucleus tumbles, creating a pattern that repeats every 15.5 hours, with a sub-pattern that repeats every 7 hours and 45 minutes. This is extraordinarily precise behavior for something that's supposed to be a loosely bound pile of ice and rock. Most comets show chaotic outgassing with jets that flare unpredictably, that turn on and off without warning, that don't follow simple rotational patterns. The fact that 3IATLAS shows such regular structured activity suggests the nucleus is more cohesive than the typical comet, that it has a strong internal structure, possibly a solid core, or a framework of stronger material holding the whole thing together. This makes sense if you think about how long it's been traveling. An object that survived billions of years of cosmic ray bombardment, micrometeorite impacts, and tidal stresses from close encounters with stars. An object that hasn't been torn apart or disrupted must be structurally robust. It must have strength integrity, some mechanism for holding itself together that goes beyond the weak self-gravity of a small body. Maybe it's sintered ice particles fused together by pressure and temperature cycling. Maybe it has a rocky component, a skeleton of silicate grains that provide structural support. Maybe it formed as a more compact object, not a fluffy aggregate, and retained that compactness over the eons. We don't know. But the regular jet activity is a clue, a hint that the interior is organized, not random. There's a beautiful irony here. The activity we're observing, the jets and the coma and the tail, are signs of the comet dying. Every gram of gas that escapes, every dust particle that's lifted off, is mass lost forever. The nucleus is eroding, shrinking, being whittled away by the sun's heat. If 3IATLAS stayed near the sun for long enough, if it orbited in the inner solar system for a few thousand years, it would lose all its ice and become a dormant asteroid, a dead rock with no volatiles left. That's the fate of all comets eventually. But because 3IATLAS is on a hyperbolic trajectory, because it's only passing through, it will only experience a few months of significant heating before it escapes back into the cold of interstellar space. The ice will refreeze. The sublimation will stop. The comet will go dormant again, preserving most of its mass, allowing it to continue its journey relatively intact. This brief flare of activity, this moment of visibility, is an anomaly in the comet's life, a temporary awakening in what has mostly been an existence of frozen silence. The jets also tell us about the surface geology. On Earth, geology is driven by plate tectonics, by volcanism, by erosion from water and wind. Comets don't have those processes. Their geology is simpler, driven by sublimation and impacts and thermal cycling. But it's still geology, still the study of surface features and how they form and change. The active regions on 3IATLAS, the spots where jets are erupting, are probably areas where the surface has cracked, where the insulating crust has broken apart, exposing fresh ice underneath. This can happen for several reasons. Thermal stress is one. As the comet heats up, the surface expands. As it cools down, it contracts. Over many cycles, this expansion and contraction can cause the crust to fracture, creating fissures and vents. Outgassing pressure is another. If gas builds up beneath the crust, it can blow a hole through weak spots like a geyser breaking through the ground. Impacts can also create active regions by excavating craters that expose subsurface ice, or by fracturing the crust around the impact site. Whatever the mechanism, the result is that some parts of the nucleus are active and some are dormant, creating the patchy, irregular outgassing we observe. The rotation period of 15.5 hours is slower than many comets, but not unusually slow. Short-period comets like Halley's rotate in anywhere from a few hours to a few days, depending on their size and shape and history of outgassing torques. Outgassing can spin a comet up, or slow it down, depending on where the active regions are located. If jets are erupting from regions near the equator, pointing tangentially, they can exert a torque that changes the rotation rate over time. This is called the rocket effect, because the escaping gas acts like a tiny rocket engine pushing on the nucleus. Over thousands of orbits, this effect can significantly alter the rotation, state-spinning some comets up to the point where they break apart, slowing others down until they're barely rotating at all. But 3IATLAS hasn't been near a star in billions of years. Its rotation rate is probably close to what it was when it was ejected from its parent system, unaltered by torques, a fossil record of the conditions at the time of ejection. Measuring that rotation rate gives us a constraint on the dynamics of the ejection event, on how the comet was spinning when it left home. As 3IATLAS approached perihelion in late October, the activity reached its peak. The coma expanded to hundreds of thousands of kilometers in diameter, a vast cloud of gas and dust surrounding the tiny nucleus, which is probably only a kilometer or two across. The tail, which had been short and stubby in July, stretched into a long, graceful streamer, pointing away from the sun, shaped by solar wind and radiation pressure. The appearance changed from week to week, sometimes even from night to night. In early September, the coma had a fan-shaped structure, asymmetric, brighter on the side, facing the sun. By mid-October, it had developed a more symmetric circular shape, with the tail extending behind. By early November, after perihelion, the tail began to fade as the comet moved farther from the sun and the outgassing slowed. This evolution is typical for comets. What's not typical is the persistence of the jet structure. Even as the overall brightness changed, even as the coma expanded and the tail grew, the jets remained visible, well-defined, rotating and precessing with mechanical regularity. That persistence is another sign of structural integrity of a nucleus that's not falling apart, not fragmenting, not disintegrating under the stress of heating. There's always a risk when a comet approaches the sun that it will break up. Tidal forces from the sun's gravity thermal, stresses from rapid heating, internal pressures from sublimating gas, all of these can exceed the weak tensile strength of a cometary nucleus and cause it to split. We've seen this happen multiple times. Comet Shoemaker-Levy 9 broke into more than 20 fragments before it crashed into Jupiter in 1994. Comet Linear disintegrated into a cloud of debris as it approached the sun in 2000. Comet Ison didn't survive its close pass by the sun in 2013, evaporating completely. So, when 3IATLAS was first discovered, when we realized it was going to come within 1.36 AU of the sun, there was concern that it might not survive. An ancient comet weakened by billions of years of cosmic ray damage might be fragile, might come apart under stress. But it didn't. It held together. It passed perihelion intact, continuing to produce jets, continuing to rotate, showing no signs of fragmentation or catastrophic outgassing. That survival is significant. It tells us the nucleus is strong, or at least strong enough to withstand one close passage by a G-type star like the sun. The dust in the coma and tail is as interesting as the gas. Dust particles are lifted off the surface by the flow of sublimating gas, carried outward at speeds of a few hundred meters per second, much slower than the gas itself, which moves at nearly a kilometer per second. Once in space, the dust particles are pushed by radiation pressure, the momentum transferred by sunlight bouncing off their surfaces. Small particles, micron-sized grains, are pushed more effectively than large particles, so they move faster and form the diffuse extended tail. Large particles, pebble-sized or bigger, barely feel the radiation pressure and fall back toward the nucleus or drift into independent orbits around the sun. The distribution of particle sizes, the dust-to-gas ratio, the composition of the grains, all of these can be measured from the way the coma and tail scatter sunlight, and they tell us about the surface properties of the nucleus and the processes that are lifting material into space. Preliminary analysis suggests 3IATLAS has a relatively low dust-to-gas ratio compared to solar system comets, meaning it's producing more gas than dust. This could be because the nucleus is rich in volatile ices and poor in rocky material, or because the dust grains are small and easily carried away, or because the surface crust has been preferentially depleted of dust over billions of years, leaving a purer ice underneath. We'll know more as the data are analyzed in detail. Have you ever watched something wake up after a long sleep? A bear emerging from hibernation, slow and sluggish, shaking off the cold? A plant sprouting after winter, tentative at first, then bursting into growth as the warmth returns. 3IATLAS is waking up in the same way, not from months of sleep, but from billions of years. The ice that's sublimating now, that's forming the jets and the coma, and the tail has been frozen solid since before the sun existed. It's older than the rocks beneath your feet, older than the oceans, older than anything, with a surface that you can point to and say this is a thing, a discrete object with a history. And now it's thawing, briefly responding to the heat of a star it encountered by chance, releasing gas that carries the chemical signature of a galaxy that was younger, simpler, less enriched in heavy elements. Every molecule that escapes is a message from the deep past, a tiny fragment of ancient chemistry returning to the cosmic ocean from which it came. The jets will fade soon. As 3IATLAS moves away from the sun, as the distance increases and the temperature drops, the sublimation will slow. The outgassing will decrease, the jets will shut down. By late January 2026, the comet will be far enough out that water ice is stable again, no longer sublimating, and the coma will collapse. The tail will disappear. The nucleus will go dark, returning to the frozen state it's been in for most of its existence. And it will drift outward past the orbit of Mars, past Jupiter, past Neptune, past the heliopause, back into interstellar space, carrying with it the ice that remains the volatiles that didn't escape the structure that survived one more close encounter with a star. It will be dormant again, invisible again, just another dark speck in the vast emptiness between stars, indistinguishable from the billions of other comets and asteroids and fragments of rock and ice that populate the galaxy. But for this brief moment, for these few months in the fall and winter of 2025, it's visible, it's active, it's showing us what an ancient comet looks like when it wakes up. And we're watching, we're measuring, we're trying to learn everything we can before it fades from view. The activity of 3IATLAS is a performance, a brief show put on by physics and chemistry, by the interaction of matter and energy, by the simple fact that ice sublimates when it gets warm. There's no intent, no purpose, no meaning beyond what we assign to it. But in the precision of the jets, in the regularity of the rotation, in the persistence of the structure over weeks and months, there's beauty. A reminder that the universe is orderly at some scales, predictable, governed by laws. We can write down and test and use to make sense of what we see. A reminder that chaos and structure coexist, that even in something as ancient and battered as 3IATLAS patterns remain. Rhythms persist. Order emerges from the dance of gravity and heat and frozen water turning to vapor. Watching the jets shift and wobble, tracking the precession, measuring the rotation period, it's easy to forget that we're doing this from 200 million miles away, that we're not there, not close, not able to reach out and touch the nucleus or fly through the coma or sample the ice directly. We're observing from a distance through layers of Earth's atmosphere, through the limitations of our instruments, through the noise and scatter and uncertainty that plague every measurement. And yet, we can do it. We can watch a kilometer-sized chunk of ice tumble through space, can measure its spin. To within a few minutes can map the locations of active regions we can't see directly, can infer the shape and structure and composition from the way light scatters and molecules glow. It's a kind of magic, this remote sensing, this ability to learn about things we can't touch. A magic built on physics and math and the patient work of people who point telescopes and write code and build models and check results and share data and argue about interpretations until the truth or something close to it emerges. The jets are alive in a way that the chemical data isn't. Chemistry tells you what something is. Activity tells you what it's doing, how it's responding, how it's changing. And 3IATLAS is changing, rapidly evolving day by day, giving us a real-time view of processes that we usually only see in snapshots, in single observations, separated by weeks or months. The Tidé Observatory Campaign. 37 nights of continuous monitoring is rare in cometary science. Most comets don't get that kind of attention. But 3IATLAS is special, and the teams observing it know it. And they're committing the time and effort to capture as much data as possible while the opportunity lasts. Every image is archived, every measurement is recorded, and years from now, long after the comet has faded and moved on, researchers will be poring over this data, extracting new insights, testing new models, discovering patterns that weren't obvious in real time. The jets we're watching now will be studied for decades, a rich data set that captures the behavior of the oldest comet we've ever seen during its brief moment in the sun. But watching is only half the story. The real work, the work that transforms pixels and spectra into knowledge, happens in observatories and control rooms, and on computer screens where light from an ancient visitor is decoded by instruments we built to see beyond ourselves. There's something profound about the act of observation, pointing an instrument at the sky and capturing light that's traveled across unimaginable distances, light that carries information encoded in wavelengths and photons information about places and times we can never physically reach. It's an act of translation, really. We're taking electromagnetic radiation, invisible patterns of energy oscillating through space, and converting it into something we can see, measure, analyze, understand. And when that light comes from something as rare as 3IATLAS, when it's bounced off the surface of an object older than our solar system, when it's been absorbed and re-emitted by molecules that formed in a protoplanetary disk 12 billion years ago, the act of observation becomes almost sacred. We're not just looking, we're witnessing. We're documenting a moment that will never repeat, a confluence of trajectories and timescales that brought this ancient comet into our sky at exactly the time when we had the technology to study it properly. And the story of how we observed 3IATLAS, the worldwide mobilization of telescopes and spacecraft and observers, is its own kind of epic, a collective human effort to squeeze every bit of knowledge from a fleeting opportunity. The first observations, as we've discussed, came from the Atlas Survey Telescope in Chile, automated software scanning the sky for moving objects, flagging anything unusual. But Atlas is a survey instrument designed for wide field coverage and rapid cadence, not for detailed follow-up. Its images showed that something was there, something moving fast on a hyperbolic orbit, something fuzzy and cometary, but they didn't have the resolution or sensitivity to reveal fine structure, to measure composition, to track the evolution of the coma and jets. For that, we needed bigger telescopes, better detectors, longer integration times. And within days of the discovery announcement, observing proposals started flooding in. Every major observatory with the capability to observe a magnitude 18 object received requests from teams wanting to study 3IATLAS. Some proposals were accepted immediately, given high priority because of the target's importance and the limited window of visibility. Others went through the normal review process and were scheduled for later dates. But everyone wanted a piece of this. Everyone wanted to contribute. The Hubble Space Telescope was one of the first to respond. Hubble is old now, launched in 1990, operating for over 3 decades, but it's still one of the most capable optical telescopes we have, especially for imaging faint extended objects like cometary comae. On July 21, 2025, Hubble's wide field camera captured images of 3IATLAS, showing the fuzzy coma in exquisite detail, resolving structure that ground-based telescopes couldn't see through the turbulence of Earth's atmosphere. The images were released publicly on August 7th, and they were stunning. The coma appeared as a soft, glowing cloud brighter toward the center, where the nucleus was hidden, fading gradually into the background. There was asymmetry, a slight elongation pointing away from the sun, the beginning of the dust tail. There were hints of jets, faint streaks extending radially from the central condensation, though they weren't as well defined as they would become later. These images were important, not just scientifically, but symbolically. They showed that 3IATLAS was real, was beautiful, was worth the effort. They gave the public something to connect with, a visual representation of the abstract concepts we'd been talking about. An ancient comet looks like this: fuzzy, gentle, ephemeral. The James Webb Space Telescope, humanity's most powerful infrared observatory, turned its instruments toward 3IATLAS on August 6th. Webb is optimized for infrared wavelengths, which are ideal for studying cold objects and molecules that emit or absorb in the infrared. Its near-infrared spectrograph, NIR spec, captured spectra of the coma, breaking down the light into thousands of individual wavelengths and measuring the absorption features of carbon dioxide, water vapor, and other molecules. The data were announced publicly on August 25th, and they confirmed what the models had predicted. 3IATLAS was rich in CO2, unusually so, with a ratio to water that was higher than typical solar system comets. This was the first direct spectroscopic evidence supporting the thick disk origin hypothesis. The first chemical fingerprint that said, this comet is different. This comet formed under different conditions than the ones we're familiar with. Webb's observations continued through the fall, tracking how the composition changed as the comet approached perihelion, as different ices activated and the sublimation rate increased. Every spectrum added to the data set, refining our understanding of what this ancient visitor is made of. Ground-based observatories contributed in ways that space telescopes couldn't. The Very Large Telescope in Chile, with its 4 8-meter mirrors and suite of advanced instruments, captured time-lapse sequences showing 3IATLAS moving against the background stars. In one 13-minute sequence, the comet's motion was clearly visible, a slow drift to the right as it traveled along its hyperbolic path. VLT also performed spectroscopy targeting specific molecules like hydrogen cyanide and ammonia, measuring their abundances, comparing them to solar system comets. The Gemini South Telescope, also in Chile, used its multi-object spectrograph to capture detailed images of the coma on August 27th, revealing the jet structure that would become the focus of so much attention. These jets, the collimated streams of gas and dust erupting from the nucleus, were the key to understanding the rotation and activity. Without high-resolution imaging from ground-based telescopes, we wouldn't have been able to track them, wouldn't have discovered the precession, wouldn't have measured the 15.5-hour rotation period. The Keck Observatory in Hawaii, with its twin 10-meter telescopes, joined the campaign in September. Keck's adaptive optics system, which uses deformable mirrors to correct for atmospheric turbulence in real time, allowed for incredibly sharp images despite observing through Earth's atmosphere. The resolution approached what you'd get from a space telescope, but with the flexibility and rapid response time that ground-based observing provides. Keck tracked 3IATLAS over multiple nights, measuring the changing brightness of the coma, the evolution of the dust tail, the subtle variations in color that hint at changes in composition or dust grain size distribution. Every night of data added another frame to the movie, another data point in the story of how an ancient comet behaves when it's warmed by a star. And then there were the spacecraft instruments not originally designed for comet observation, but repurposed when the opportunity arose. NASA's Stereo mission, a pair of spacecraft orbiting the sun and designed to study solar activity, caught glimpses of 3IATLAS as it passed through their fields of view. Stereo's wide-angle cameras, built to track coronal mass ejections and solar wind structures, weren't optimized for faint comets, but they could still detect 3IATLAS against the background glow of the zodiacal light. The images were noisy, hard to interpret, but they provided a unique perspective, a view from a different vantage point than Earth-based telescopes, which helped refine the orbit and constrain the shape of the dust tail. The Solar and Heliospheric Observatory, SOHO, another sun-watching spacecraft, contributed similar data. These weren't glamorous observations. They weren't going to produce pretty pictures for press releases, but they were valuable, filling in gaps, providing cross-checks, ensuring that the orbital calculations were as accurate as possible. Perhaps the most unexpected observation came from the ExoMars Trace Gas Orbiter, a spacecraft circling Mars and designed to study the Martian atmosphere. On October 3rd, when 3IATLAS passed relatively close to Mars, at a distance of 0.19 AU, about 18 million miles, ExoMars turned its camera toward the comet and captured images showing it against the Martian sky. The perspective was bizarre, otherworldly. We're used to seeing comets from Earth's vantage point, always looking outward into the solar system, or inward toward the sun. But seeing a comet from Mars, from another planet, that's rare. The images showed 3IATLAS as a faint streak background, stars trailing because the camera was locked onto the fast-moving comet, the coma and tail clearly visible despite the distance. These images didn't add much scientifically that we couldn't get from Earth-based telescopes, but they were a reminder of how far our observational capabilities have spread, how we've built eyes all over the solar system, watching from different perspectives, capturing views that expand our understanding of space and motion and scale. Amateur astronomers played a role too. When 3IATLAS brightened to around magnitude 11 in late October and early November, it became accessible to moderately equipped amateur telescopes, 8-inch or 10-inch reflectors with good cameras and dark skies. Dozens of amateur observers around the world submitted images to databases like the Minor Planet Center and the Comet Observation Database, contributing photometric measurements, position fixes, visual descriptions of the coma and tail. These observations are valuable because they provide continuous coverage, filling in the gaps between professional observing runs. Professional telescopes have limited time, tightly scheduled, often with weeks between observations of a given target. Amateurs can observe every clear night, tracking changes day to day, catching transient events like outbursts or sudden brightenings that might be missed by scheduled programs. The collective effort, thousands of hours of observing time donated by people who do this for love of the sky, added texture and depth to the dataset, ensuring that no major event went unrecorded. The Tidy Observatory campaign deserves special mention. 37 consecutive nights of monitoring from late August through September, dedicated to tracking the jets and measuring the rotation. This kind of sustained effort is rare in astronomy, where telescope time is precious and competition is fierce. But 3IATLAS was worth it. The team at Tidy, using the relatively modest 2-meter twin telescope, produced some of the most important data of the entire observing campaign. They measured the jet wobble, the precession period, the changing orientation of the active regions. They documented how the coma evolved from a fan-shaped structure to a more symmetric distribution. They captured the moment when the dust tail became clearly visible, stretching away from the nucleus like a ribbon in the solar wind. And they did it with patience and precision, night after night, building up a time series dataset that will be analyzed for years to come. This is what good science looks like. Not flashy press releases and dramatic discoveries, but careful, methodical observation, attention to detail, commitment to seeing a project through even when the target is faint and the weather is bad and the data reduction is tedious. Spectroscopy was happening at multiple wavelengths, each range revealing different aspects of the comet's composition. Ultraviolet spectroscopy from Hubble targeted emissions from oxygen and sulfur elements that glow brightly in the UV when they're ionized by sunlight. Visible light spectroscopy from ground-based telescopes like VLT and Keck focused on the CN-C2 and C3 radicals, fragments of larger organic molecules that break apart in the coma and emit characteristic green and blue light. Infrared spectroscopy from Webb and ground-based instruments like the NASA Infrared Telescope Facility probe the vibrations of molecules like water, carbon dioxide, methane, and ammonia, measuring their abundances and temperatures. Radio observations from the James Clerk Maxwell Telescope in Hawaii detected the rotational transitions of hydrogen cyanide and other molecules, providing independent measurements of outgassing rates and composition. Each wavelength range, each technique, each instrument contributed a piece of the puzzle. No single observation could give the complete picture. It took the combined effort, the integration of data across the electromagnetic spectrum, to build a comprehensive understanding of what 3IATLAS is and where it came from. There's a misconception that needs addressing. When people hear that astronomers are studying a comet from another star system, they sometimes imagine we're looking for signs of alien technology, searching for anomalies that might indicate artificial origin. And yes, some speculation did surface online, fueled by the comet's unusual properties, and the fact that the previous interstellar visitor, Oumuamua, sparked similar debates. But the professional astronomical community approached 3IATLAS with the assumption that it's a natural object, a comet, and the observations have consistently supported that assumption. Everything we see, the coma, the tail, the jets, the spectroscopic signatures, the rotation, all of it is consistent with a natural cometary nucleus made of ice and rock sublimating under solar heating. There's no evidence of artificial structure No anomalous accelerations that can't be explained by outgassing. No radio signals, no geometric shapes, nothing that requires invoking non-natural explanations. This isn't disappointing. This is exactly what we'd expect. The universe is full of comets. Some of them get ejected from their parent systems and wander the galaxy. We're seeing one of those wanderers. It's extraordinary because of its age and origin, not because it's artificial. The observations also served a practical purpose beyond pure science. Tracking 3IATLAS, precisely refining its orbit, predicting where it would be weeks and months in advance. All of this required accurate astrometry position, measurements against the background stars. Every image from every telescope contributed to this, allowing orbital dynamicists to improve the calculations, to reduce the uncertainties, to ensure that future observations would know exactly where to point. By November, the orbit was known well enough that we could predict the comet's position to within a few arc-seconds weeks in advance, a testament to the power of combining data from multiple sources and refining the solution iteratively. This precision is important not just for 3IATLAS, but for future interstellar objects. We're learning how to track these things, how to coordinate observations, how to maximize the scientific return from brief opportunities. The next time an interstellar visitor passes through, we'll be better prepared, faster to respond, more efficient in our use of telescope time. As 3IATLAS moved past perihelion and began its journey outward, as it faded and the observing conditions became more challenging, the focus shifted from imaging and spectroscopy to photometry, measuring the total brightness and how it changed over time. Photometry is simpler than spectroscopy, requires less light, can be done with smaller telescopes. It tells you how much material the comet is producing, how fast the sublimation rate is declining as the comet moves away from the sun. By tracking the brightness curve, the light curve astronomers can model the comet's activity, estimate the size of the nucleus, understand how different ices shut down at different temperatures. This is the unglamorous tail end of an observing campaign, the slow fade out, but it's important. The full story includes not just the peak brightness, but the decline, not just the approach, but the departure. By late December 2025, 3IATLAS had faded to magnitude 14 or 15, too faint for most amateur telescopes, requiring professional instruments and long exposures to detect. The coma was shrinking. The tail was disappearing. The jets had stopped the sublimation rate dropping below the threshold where collimated outflows could form. By mid-January 2026, it was magnitude 17, barely visible. Even in large professional telescopes, a faint smudge indistinguishable from a distant galaxy except for its motion. And by late January, it crossed the threshold where observation was no longer practical, too faint, too far, too much effort for too little return. The window closed. The campaign ended. Telescopes moved on to other targets, other discoveries, other questions. 3IATLAS continued its journey outward, silent and invisible, receding into the darkness from which it came. But the data remain. Thousands of images, hundreds of spectra, millions of photons captured and recorded and stored in digital archives waiting to be analyzed, reanalyzed, compared, questioned, understood. The observation phase lasted about 7 months, from July 2025 to January 2026. But the analysis phase will last years, maybe decades. Every image can be reprocessed with better algorithms. Every spectrum can be recalibrated with updated atomic data. New models can be applied to old data sets, extracting insights that weren't apparent the first time through. This is the nature of modern astronomy. The observation is the beginning, not the end. The real work happens afterward in offices and computer labs, where researchers pore over the data, writing papers, debating interpretations, building understanding pixel by pixel, wavelength by wavelength. Think about what it means that we could do this. that we could mobilize a global network of telescopes, space-based and ground-based, professional and amateur optical and infrared and radio and ultraviolet, and point them all at a single faint object moving through our sky. That we could coordinate schedules, share data, compare results, build a comprehensive picture from thousands of individual observations. That we could do it fast, responding to the discovery within days, ramping up to peak intensity within weeks, maintaining the effort for months. This is a triumph of collaboration, of shared scientific culture, of infrastructure built over decades by agencies and institutions and individuals who believed in the value of studying the universe. No single telescope could have done this. No single team could have done this. It took the community. And the community delivered. The observations of 3IATLAS will stand as a benchmark for how to study interstellar objects. We learned what works, what doesn't, what instruments are most valuable, what wavelengths are most informative, how to balance breadth and depth, survey and follow-up. The next interstellar visitor will benefit from this experience. We'll know to trigger certain observations immediately, to prioritize certain measurements, to avoid certain pitfalls. We'll be faster, more efficient, more effective. And if we're lucky, if the next one is brighter or closer or slower moving, we might get even better. Data might answer questions that 3IATLAS left open, might push our understanding another step forward. But even if we never see another interstellar comet as old as this one, even if 3IATLAS remains the record holder for age and ancient origin, the observations we've made are enough. Enough to confirm the thick disk hypothesis, enough to measure the chemistry, enough to track the activity, enough to know that we found something truly special and documented it properly. We witnessed a 12 billion year journey ending or pausing in our sky. And we captured it, preserved it, turned light into data, data into knowledge, knowledge into understanding. The light we collected from 3IATLAS carried more than information about chemistry and motion. It carried the weight of time, the signature of epochs we can barely imagine, the echo of a galaxy that was young when this comet formed and is now ancient, settled, familiar. And in studying that light and decoding those echoes, we touch something larger than ourselves. Now, the observations are done, the data set's archived, and the question shifts from what we saw to what it means. What this ancient visitor teaches us about the galaxy and our place within it. Sometimes a single discovery changes how we see everything else. Not because it rewrites the laws of physics or overthrows established theory, but because it opens a door we didn't know was there, reveals a perspective we hadn't considered, shows us that the universe is stranger and richer and more layered than we imagined. 3IATLAS is one of those discoveries. On the surface, it's just a comet, a chunk of ice and rock, not particularly large, not particularly bright, following the same physical laws as every other comet we've studied. But it's where it came from, when it formed what it represents, that makes it extraordinary. Because 3IATLAS isn't just teaching us about comets. It's teaching us about the galaxy itself, about how stars and planets form across billions of years, about how material moves through space and time, about the hidden architecture of the Milky Way that we're only beginning to map. And the implications ripple outward, touching questions about planetary formation, about the distribution of water and organic molecules, about the possibility of life in places and times we've never seriously considered. Let's start with the most immediate implication. If 3IATLAS came from the thick disk, if it formed around a star that's 8 or 10 or 12 billion years old, then thick disk stars can produce comets. That might seem obvious, but it wasn't a given. We've never observed a thick disk planetary system up close. We've found exoplanets around old stars, but detecting planets is hard enough. Detecting comets around other stars is essentially impossible with current technology because they're too small and too faint. So we've had to infer to assume, based on theory, that the same processes that make planets and comets around young metal-rich stars, like the Sun, also operate around old metal-poor stars. And 3IATLAS is the evidence. It's proof that thick disk stars had protoplanetary disks, that those disks contained ice and dust, that comets formed and were ejected just like in our own solar system. This might seem like a small point, but it's foundational. It means the planet formation process is robust, persistent, operating across a wide range of stellar environments and cosmic epochs. It means that wherever there are stars, there are probably planets. And wherever there are planets beyond the snowline, there are probably comets. The water richness of 3IATLAS has implications for habitability in the ancient galaxy. Water is essential for life, as we know it. It's the solvent in which biochemistry happens, the medium that allows molecules to move and interact and assemble into complex structures. On Earth, life arose in water, probably in the oceans, or in hydrothermal systems where water was abundant. And the water on Earth, at least some of it, probably came from comets. During the late heavy bombardment about 4 billion years ago, the inner solar system was pummeled by impacts from comets and asteroids, and those impacts delivered water, carbon, nitrogen, the raw materials that would eventually become oceans and atmospheres and organisms. If thick disk stars had water-rich comets like 3IATLAS, if those comets were delivered to planets during the equivalent of the late heavy bombardment in those ancient systems, then those planets could have had oceans. They could have been habitable. They could have developed life billions of years before life arose on Earth. This is speculative, of course. We have no direct evidence of ancient life around thick disk stars. We don't even know if any of those stars still have intact planetary systems, or if the planets were destroyed or ejected or swallowed when the stars evolved off the main sequence and swelled into red giants. But the pieces are there, the ingredients. Water delivered by comets, carbon and nitrogen and phosphorus. The other elements life needs also present in comets. Energy from the host star, available for billions of years, while the star burns steadily on the main sequence. Time, enormous amounts of time for evolution to work. For complexity to arise, for life to perhaps reach levels we can't imagine, because we've only seen 4 billion years of evolution on one planet. And these hypothetical systems had twice that, maybe more. If life arose on a planet orbiting a thick disk star 9 billion years ago, what would it look like now? Would it still be microbial, simple, limited by environmental constraints? Or would it have evolved into something unrecognizable, something so far beyond what we are, that we couldn't even identify it as life? We don't know. We can't know. But 3IATLAS, with its water ice and organic molecules and ancient origin, is a reminder that the conditions for life have existed in the galaxy for much longer than they've existed on Earth. There's a common mistake people make when thinking about the search for extraterrestrial life. They focus on planets around sun-like stars, stars similar to ours in age and composition, because that's the environment we know works. But the galaxy is old. Most of its stars formed long before the sun. And if those older stars could have habitable planets, if life could have arisen around them, then the majority of life in the galaxy could be much older than life on Earth. We might be the newcomers, the late arrivals, the young civilization, in a galaxy that's already full of ancient biospheres, ancient ecologies, ancient intelligences, if such things exist. 3IATLAS doesn't prove this, but it shifts the probability space. It shows that the building blocks were there early, that the processes that enable habitability were operating when the galaxy was young, that we shouldn't assume life is a recent phenomenon just because life on Earth is relatively recent. The implications are profound for SETI, for the search for extraterrestrial intelligence. If advanced civilizations exist, they might be billions of years older than us. They might have perspectives, technologies, understandings that are as far beyond ours as we are beyond bacteria. And they might be out there right now observing the same galaxy. We are seeing the same interstellar comets, drawing the same conclusions about the persistence of habitability across cosmic time. Another implication concerns the Vera C. Rubin Observatory and the future of interstellar object detection. When Matthew Hopkins and his colleagues developed the Oxford model, they made predictions about how many interstellar objects we should expect to find once we have the right instruments. Before 3IATLAS, the predictions were conservative, maybe a few per year, mostly from the thin disk, mostly similar to Borisov and Oumuamua. But the discovery of a thick disk object, something older and rarer, suggests the population might be larger and more diverse than we thought. Rubin, with its enormous field of view and sensitive detectors, is expected to begin its 10-year survey in the near future. And based on the revised predictions incorporating what we've learned from 3IATLAS Rubin, might find between 5 and 50 interstellar objects over the course of the survey. Maybe more if we're lucky. Each one will add to the data set, refine the models, improve our understanding of how these populations are distributed and how they evolve. Some will be young objects from the thin disk. Some might be ancient objects from the thick disk, like 3IATLAS. A few might come from even stranger places, from the galactic halo, from disrupted globular clusters, from regions we haven't even considered. And each one will carry information, chemical signatures, kinematic clues that tell us about parts of the galaxy we can't visit, about epochs we can only study through these wandering messengers. The discovery also has implications for how we think about galactic mixing. The galaxy isn't static. Stars orbit the galactic center, but they don't all orbit on perfect circular paths in a flat disk. They have random motions, eccentric orbits, vertical oscillations. Over billions of years, this random motion mixes the stellar populations, blurring the boundaries between the thin disk and thick disk and halo. And the same mixing happens with interstellar objects. Comets ejected from thick disk stars don't stay in the thick disk. They wander, crossing through the thin disk, passing through the halo, encountering stars from different populations, swapping energy and momentum through gravitational interactions. 3IATLAS is a product of that mixing. It formed in the thick disk, but it's passing through the thin disk now through our solar system, which is very much a thin disk system. And there are probably thin disk comets wandering through the thick disk and halo comets passing through both disks, a constant circulation of material that connects different parts of the galaxy that prevents any region from being truly isolated. This mixing has implications for chemical evolution, for how elements get distributed, for how the metallicity of different regions changes over time. It's not just stars that enrich the interstellar medium. It's also comets, asteroids, dust grains, all the debris of planetary systems wandering and eventually being destroyed or incorporated into new systems, adding their atoms to the next generation. There's also the question of how common ejection is. For every comet we detect passing through the solar system, how many were ejected from our own system and are now wandering the galaxy? The answer depends on the dynamics of planetary formation and evolution. In our solar system, gravitational interactions with the giant planets, especially Jupiter and Saturn, have ejected countless objects over the past 4.5 billion years. Some ended up in the Oort cloud, a distant reservoir of comets that surrounds the Sun. Some achieved escape velocity and left entirely, becoming interstellar wanderers. The same processes must happen in other systems. Young planetary systems are chaotic, with planets migrating with resonances sweeping through the disk with close encounters and ejections. Most of the solid material in a protoplanetary disk, probably 95% or more, either falls into the star, accretes onto planets, or gets ejected. And the ejected fraction becomes the interstellar population, the comets and asteroids that drift through the galaxy, waiting to be captured or observed by someone else. If every star ejects billions or trillions of objects, if there are hundreds of billions of stars in the galaxy, then the interstellar population is vast, unimaginably vast. Most of it is invisible, too small and dark to detect, but occasionally one passes close enough to the Sun that we can see it, and we get a glimpse of that hidden population, a census sample of one drawn from an ocean of wanderers. The seeding hypothesis is another implication worth exploring. We've talked about panspermia, the idea that life might spread from planet to planet via comets or meteorites, but usually in the context of our own solar system or nearby stars. The discovery of ancient interstellar comets like 3IATLAS raises a different possibility. What if life arose on a planet around a thick disk star 8 or 9 billion years ago, and that life somehow got ejected into space, embedded in rocks or ice, and traveled across the galaxy, eventually landing on a younger planet where it took root? It sounds like science fiction, but the physics is plausible. Microorganisms can survive in the vacuum of space if they are protected from radiation, and ice provides excellent protection. A comet could carry frozen microbes for billions of years, preserving them in a state of suspended animation. And if that comet impacted a planet with liquid water and a stable environment, the microbes could potentially revive and begin reproducing. We don't have evidence this has happened. The genetic record on Earth shows a clear lineage going back to a single common ancestor with no obvious signs of an extraterrestrial origin. But the absence of evidence isn't evidence of absence. And if life did spread via panspermia, if there's a connected biosphere spanning multiple stars and epochs, then the tree of life might be much larger and older than we've imagined, with branches on planets we'll never see rooted in a past that predates our solar system. Let's bring this back to something more concrete. The study of 3IATLAS is helping us refine our models of protoplanetary disk chemistry. We have good models for how disks around sun-like stars evolve, how ices condense, how dust grains grow and drift, and eventually form planets. But those models are tuned to solar composition, solar metallicity, solar-type stars. When we try to apply them to lower metallicity stars, to thick disk stars, the predictions become less certain. Lower metallicity means less dust, which means different disk opacity, which affects temperature profiles and snowline locations. It means different chemical abundances, which affects what molecules can form and in what proportions. The observations of 3IATLAS, the water richness, the elevated CO2, the unusual metal ratios, are tests of those models. They tell us whether our understanding of disk chemistry is robust enough to handle different environments, or whether we need to revise our assumptions. And the early indications are that revisions might be needed. The chemistry isn't quite what we expected. The details are off, which means there's more to learn, more complexity to uncover, more physics hiding in the data. There's a philosophical dimension to this as well. 3IATLAS is a reminder that the galaxy has a history, that the conditions today are not the conditions that have always been that the universe evolves. We live in a mature galaxy, a galaxy that's been around for 13 billion years, that's been through multiple generations of star formation, that's enriched in heavy elements and settled into a stable structure. But most of the galaxy's history happened before we arrived. Most of the stars have already formed. Most of the planets have already accreted. Most of the life, if it exists, has already arisen and evolved and perhaps gone extinct. We're late to the party. And objects like 3IATLAS are the guests who have been here since the beginning, who remember what it was like when the music was louder, when the lights were brighter, when everything was younger and wilder and less predictable. By studying them, we're learning about epochs we can't observe directly, about a galaxy that existed long before us, that set the stage for everything that followed, including us. The discovery also has practical implications for planetary defense, though not in an immediate sense. Planetary defense is concerned with near-Earth asteroids and comets that might pose an impact threat. Interstellar objects like 3IATLAS aren't a threat, because their velocities are so high that they pass through the inner solar system quickly without lingering, without getting captured into Earth-crossing orbits. But the mere fact that these objects exist, that they pass through regularly, raises questions about whether we'd be able to detect and track a genuinely hazardous interstellar impactor if one ever came our way. The answer, based on our experience with 3IATLAS, is probably yes, if it's large enough and we have enough warning time. But if an interstellar object were on a collision course with Earth and we only detected it a few months out, there wouldn't be much we could do. It's a low probability scenario, not something to lose sleep over, but it's worth thinking about as we develop our detection networks and our response capabilities. One of the most exciting implications is what 3IATLAS tells us about the possibility of visiting interstellar space with probes. If interstellar comets pass through the solar system regularly, if Rubin finds dozens of them over the next decade, then we might have opportunities to send spacecraft to intercept them to fly by, or even rendezvous to study them up close in ways that ground-based telescopes never could. Missions like this have been proposed for future interstellar visitors. They'd require rapid response, fast spacecraft, innovative propulsion, but they're feasible with technology we're developing now. And the scientific return would be immense. Imagine a spacecraft flying through the coma of an ancient thick disk comet, sampling the gas and dust, analyzing the composition in situ, maybe even landing on the nucleus and drilling into the ice to retrieve a core sample. That sample would be a direct piece of the ancient galaxy, uncontaminated by Earth's environment, preserved in the conditions it formed under a treasure beyond price for understanding our cosmic origins. We didn't have time to mount such a mission for 3IATLAS. The discovery came too late, the technology wasn't ready, the funding wasn't in place, but the next one may be. Or the one after that. The era of interstellar comet exploration is beginning, and 3IATLAS is the herald. Before we move toward the end, before we say goodbye to this ancient visitor, consider what we've learned from a single object. One comet, one chance encounter, one brief passage through our sky, and we've gained insights into the thick disk, into ancient star formation, into protoplanetary disk chemistry, into the distribution of water and organics, into the population of interstellar wanderers, into the history of the galaxy itself. That's the power of observation, of measurement, of careful science applied to rare opportunities. Every object in space is a teacher if we pay attention, if we ask the right questions, if we're willing to do the work of decoding what the light and the motion and the chemistry are telling us. 3IATLAS taught us well, and the lessons will echo for decades, shaping research programs, inspiring new missions, guiding the next generation of astronomers who will study the comets we haven't found yet, the wanderers still hidden in the dark, waiting for their moment to pass through our light. The implications reach beyond astronomy, beyond science, into the realm of perspective and wonder. Knowing that something older than our world is drifting past, that we're sharing space with a fragment of the galaxy's deep past, changes how we see ourselves. We're not separate from the cosmos, we're part of it. We're made of the same atoms, subject to the same forces, participants in the same grand story of matter and energy evolving over time. And sometimes, if we're very lucky, the story comes to us. But all stories, even the longest, approach their endings. And 3IATLAS, having shown us what it came to show, is fading now, returning to the silence from which it briefly emerged. There's a moment in every goodbye when you realize it's really ending. Not the abstract knowledge that something is temporary, that all things pass, but the visceral feeling of watching something slip away, of knowing you won't see it again. At least not in this lifetime, not in this form. For 3IATLAS, that moment came quietly without fanfare, sometime in late January 2026. The comet didn't vanish suddenly. It didn't explode or fragment or do anything dramatic. It just faded. Night by night, observation by observation, it grew dimmer, smaller, harder to see, until finally it crossed the threshold where even the largest telescopes couldn't gather enough photons to distinguish it from the background noise of the universe. And then it was gone, not destroyed, not ended, just invisible. Still out there, still traveling, still carrying its ancient ice on a journey that will continue for billions of years, but gone from our sight, gone from our reach. Return to the darkness between stars, where it spent most of its existence, where it will spend the rest. The last confirmed observation came from a research team using one of the Keck telescopes in Hawaii on January 28, 2026. By that point, 3IATLAS was magnitude 18.5, right at the edge of detectability, a faint smudge requiring multiple long exposures stacked together to even confirm it was there. The coma had collapsed entirely. The jets had shut down weeks earlier as the comet moved past Jupiter's orbit, and the solar heating dropped below the threshold for water-ice sublimation. What remained was probably just the bare nucleus, a dark, inert chunk of ice and rock, maybe a kilometer across, reflecting only the faint sunlight that reached it at that distance. The researchers captured a few final position measurements, added them to the orbital database, and that was it. The observation log closed, the campaign ended, telescopes pointed elsewhere, and 3IATLAS continued on, unobserved, unmonitored, alone, again as it had been for billions of years before we found it. Where is it now? Somewhere past the orbit of Saturn, heading outward, traveling at 58 kilometers per second relative to the Sun. By the time you hear these words, it will be even farther. In a year, it will cross the orbit of Uranus. In 5 years, Neptune. In 10 or 15 years, it will reach the heliopause, the boundary where the Sun's influence ends and interstellar space begins, where the solar wind collides with the thin gas of the interstellar medium and creates a shock wave, a bow wave, like a boat pushing through water. And then it will be truly gone, back into the galactic ocean, back into the realm between stars where distances are measured in light years and time scales are measured in millions of orbits around the galactic center. It won't remember us. It can't. It's not alive. It doesn't have memory or awareness or any sense that something significant happened during its brief passage through our solar system. But we'll remember it. We'll carry the data, the images, the spectra, the stories forward into our own future, learning from them, building on them, using them to understand not just 3IATLAS, but the galaxy it came from, and the universe that contains both of us. Think about the journey ahead of it. 3IATLAS is on a galactic orbit now, moving through the Milky Way at about 60 kilometers per second, relative to the local standard of rest, the reference frame defined by the average motion of nearby stars. At that speed, it takes about 200 million years to complete one orbit around the galactic center. If it's 12 billion years old, it's completed about 60 orbits. 60 circuits through the disk, 60 passages through the spiral arms, 60 cycles of rising above the plane, falling back down, crossing through again. And it will complete dozens more before the sun itself dies, before the Earth is swallowed by the red giant our star will become, before all the familiar constellations have drifted apart and reconfigured into patterns that would be unrecognizable to us. 3IATLAS will outlast us. It will outlast our solar system. It will drift through a future galaxy we can't predict, past stars that haven't formed yet, through regions that are empty now, but might be dense stellar nurseries billions of years hence. And maybe it will pass through another solar system encounter, another star with planets, with beings who look up and wonder, who build telescopes and detectors and models, who find it and study it and marvel at how old it is, how far it's traveled, how much it's survived. There's a poetic justice in that possibility, that 3IATLAS might give to someone else what it gave to us, a glimpse of the deep past, a messenger from epochs that can't be visited, only inferred, a reminder that the universe is older and stranger than it appears from any single vantage point. We were the recipients this time. We were the ones who happened to be in the right place at the right time with the right tools. But we're not special in any cosmic sense. We're just one more stop on an endless journey, one more set of observers in a long chain that stretches back to whenever the first beings looked up and wondered about lights in the sky. And if there are observers in the future, if intelligence persists in the galaxy, they'll be part of that chain too, studying their own interstellar visitors, learning their own lessons, asking their own questions about origins and destinations, and the nature of time. The data from 3IATLAS will be analyzed for years. Already papers are being written, hypotheses, tested models, refined. The first results? The confirmation of the thick disk origin, the age estimates the chemical composition. Those were published quickly in the months following the discovery. But the deeper work takes longer. Researchers are still combing through the spectroscopic data, looking for faint absorption lines that might reveal trace molecules, isotopic ratios that might constrain formation conditions. They're still analyzing the photometry, the brightness measurements over time, to model the shape and rotation state of the nucleus with higher precision. They're still comparing 3IATLAS to solar system comets to the other interstellar visitors, building frameworks for understanding how cometary populations vary across different stellar environments. And they're still arguing in the best scientific tradition about what the data mean, what conclusions are justified, what questions remain open. This is how science works. Not in sudden revelations, but in slow, careful accumulation of understanding and debates and revisions and incremental improvements in the patient work of turning observations into knowledge. There will be surprises, there always are. Someone will notice something in the data that everyone else missed, some subtle pattern or unexpected correlation. And it will open a new line of inquiry, prompt new observations of future objects, revise our models in ways we didn't anticipate. That's one of the joys of studying something rare. You're not just confirming what you already know. You're exploring, discovering, finding things that don't fit, that challenge your assumptions, that force you to think harder and look deeper. 3IATLAS has already delivered surprises. The water richness was somewhat expected, but the degree of it was higher than predicted. The nickel-to-iron ratio is still puzzling, not easily explained by current models. The structural integrity, the persistence of the jets, the fact that the comet survived billions of years without fragmenting, all of that raises questions about cometary physics that we're still working through. And there will be more surprises buried in the data, waiting for the right analysis, the right question, the right moment of insight. Future interstellar visitors will be compared to 3IATLAS. It's become the benchmark, the reference case for thick disk objects, the way Borisov is the reference case for thin disk objects, and Oumuamua is the reference case for whatever Oumuamua was still debated, still mysterious in its own way. When the next ancient comet is discovered, when Rubin finds an object with a steep galactic trajectory and high vertical velocity, the first thing researchers will do is compare it to 3IATLAS. Is it similar, different? What did the differences tell us about diversity in the thick disk population? About variations in formation environments, about how comets evolve over time? Every new object adds context, reduces the risk that we're overinterpreting a single case, that we're seeing something unusual and mistaking it for typical. 3IATLAS might be representative of ancient comets, or it might be an outlier, a weird one with properties that are rare even among thick disk objects. We won't know until we have a larger sample. But the fact that we found even one, the fact that we were able to study it in this much detail is a triumph. There's a lesson here about patience and readiness. The discovery of 3IATLAS happened because we built the infrastructure. Because we invested in survey telescopes like ATLAS, designed to scan the sky repeatedly to catch transient events to flag anything unusual. Because we developed the software to process images in near real time, to detect motion, to distinguish comets from asteroids from noise. Because we trained a generation of astronomers who know how to respond quickly, how to coordinate observations, how to maximize the science return from brief opportunities. None of this was built specifically for interstellar comets. ATLAS was designed for planetary defense, for finding near-Earth asteroids that might pose an impact threat. But good infrastructure is versatile. It solves the problem it was designed for, and also solves problems we didn't anticipate. And when 3IATLAS appeared, when the algorithms flagged it, and the follow-up teams confirmed it, the system worked. We were ready. And because we were ready, we didn't miss it. We captured it, studied it, learned from it. Imagine if this had happened 50 years ago, before we had the technology. we would have missed it entirely. It would have passed through the solar system, unseen, unrecorded, just another faint moving object that no one noticed. The science would have been lost. The opportunity would have been wasted. But we caught it. We were prepared, and that preparation paid off. The story of 3IATLAS is also a story about collaboration. No single person discovered it, studied it, understood it. It took a community. The Atlas team in Chile, who first detected it, the orbital dynamicists who calculated its trajectory, Matthew Hopkins and Chris Lintott, and their colleagues who developed the models and estimated the age, the spectroscopists who measured composition, the imaging teams who tracked the jets and the rotation, the amateurs who contributed photometry, the instrument scientists who built Hubble and Webb and VLT and Keck and all the other telescopes that observed it, the theorists who interpreted the data, the writers who communicated the findings to the public, the students who learned from it, who will carry the knowledge forward, who will be the next generation of researchers studying the next interstellar visitors. Science is collaborative by nature, but the study of 3IATLAS exemplified it. People from different countries, different institutions, different specializations working together toward a common goal, sharing data, building on each other's work, pushing the frontier of understanding forward, one observation, one paper, one conversation at a time. And what about us sitting here listening to this story? What do we take from it? Maybe it's a sense of scale, a reminder that human time scales, the decades we live, the centuries our civilizations last, are brief compared to the time scales of the cosmos. 3IATLAS has been traveling for longer than our species has existed, longer than primates have existed, longer than mammals, longer than the continents have been in their current configurations. It's a piece of deep time, and encountering it even from a distance, even through the mediation of telescopes and data, is an encounter with something that transcends our ordinary experience of duration. Or maybe it's a sense of connection. We're part of the same galaxy as 3IATLAS. We're made of the same elements forged in the same types of stars scattered by the same supernovae. The atoms in your body and the atoms in that comet share a common ancestry, a lineage that goes back to the Big Bang and forward to whatever the universe becomes. We're not separate from the cosmos. We're embedded in it, participants in its evolution, witnesses to its wonders. Or maybe it's simply wonder itself, the capacity to be amazed, to be curious, to want to understand. That's a deeply human trait, maybe the trait that defines us most clearly. And 3IATLAS, with its age and its journey and its chemistry, is an object worthy of wonder. Have you ever thought about what it means to be the generation that sees these things? The generation that discovers interstellar visitors, that images exoplanets, that detects gravitational waves, that peers back to the first galaxies with Webb that sends robots to Mars and probes to the outer planets, and maybe someday spacecraft to the stars. We live in an extraordinary time. Not extraordinary because we're special, but because the tools have finally caught up to the questions, because the technology has reached the point where we can study the universe in ways that were impossible even a few decades ago. Our ancestors looked at the same sky, we saw the same stars, wondered the same questions. But they didn't have the tools to answer them, we do. And with those tools, we're building a picture of the cosmos that's richer and stranger than anyone imagined. 3IATLAS is one brush stroke in that picture. A small one maybe in the grand scheme, but a beautiful one. A detail that adds depth and texture and meaning to the larger image we're constructing. The comet is gone now, fading into the interstellar night, but the light it reflected, the molecules it released, the data it provided, those remain. Stored in archives, analyzed in papers, taught in classrooms, shared in conversations like this one. We captured a moment. We froze it in data, and that data will last as long as we do, as long as we preserve it, as long as we care about the stories it tells. In a sense, 3IATLAS is still here, still with us. Not as a physical object, but as information, as knowledge, as a chapter in the story. We're writing about the galaxy and our place in it. And that's a kind of immortality, isn't it? Not for the comet, which doesn't care, but for the encounter, for the meeting between an ancient wanderer and a young species that had just learned how to see beyond itself. There will be more visitors. The galaxy is full of wanderers, and as our detection capabilities improve, as Reuben begins its survey, as new telescopes come online, we'll find them. Some will be like 3IATLAS, ancient and fascinating. Some will be like Borisov, more typical, more familiar. Some will be like Oumuamua, strange and hard to categorize, pushing the boundaries of what we think we know. Each one will teach us something. Each one will add to the data set, refine the models, expand our understanding. And each one will be a gift, a brief opportunity to study something that came from elsewhere that carries information we can't get any other way. We're living at the beginning of the era of interstellar object science. The first few have been found. The techniques are being developed. The infrastructure is being built. And the future, the coming decades, will bring a flood of discoveries, a census of the galaxy's wandering population, a map of how material moves through space and time on scales we're only beginning to grasp. So, we say goodbye to 3IATLAS. We watch it fade. We thank it in our way for what it brought us, for the water ice that formed around a star we'll never see, for the journey that lasted longer than worlds, for the chemistry that tells us about the ancient galaxy, for the jets and the rotation and the persistent structure that revealed the comet's strength, for the opportunity to witness something rare and precious and fleeting. And as it drifts back into darkness, as the distance grows and the light fades and the solar system shrinks to a point behind it, we turn our attention forward to the next discovery, to the questions that remain, to the work of understanding a universe that keeps revealing itself layer by layer, mystery by mystery, one careful observation at a time. The universe is patient. It's been here for 13.8 billion years. It will be here long after we're gone. But it's also generous. It offers glimpses, opportunities, moments when something extraordinary passes close enough to see, to study, to learn from. We were lucky to catch 3IATLAS, lucky to have the tools, the knowledge, the collective will to observe it properly. And we'll be lucky again when the next visitor comes, when the next ancient messenger arrives carrying stories from the deep past. The sky is vast and full of wonders, and we're learning slowly but surely how to read them. Thank you for drifting here with us, for spending these quiet hours following a comet older than the sun, for being willing to think about time scales that dwarf our own, for caring about chemistry and orbits and the slow dance of matter through space. If this story moved you, if it sparked something, a question, a curiosity, a sense of connection to the larger cosmos, then carry that forward. Look up on a clear night. Think about what's out there moving unseen. Think about the light traveling toward us from distant stars carrying information about places we'll never visit. Think about the atoms in your body forged in stellar furnaces, scattered by explosions, gathered into planets, and eventually into you. You're part of this. We all are. Participants in the grand experiment of the universe becoming aware of itself. And that's a beautiful thing, a sacred thing, a reason to wonder and to learn and to keep asking questions. Sleep well, dream gently, and when you wake, the galaxy will still be here, still turning, still full of stories waiting to be discovered. We'll be back soon with another journey, another quiet exploration of the cosmos and the wonders it holds. Until then, rest. The stars will wait. Good night.